The following message is best viewed on an oscilloscope.
So, good afternoon. Welcome to the second session of the Quark and Lepton Flavor Physics. So just to remind the speakers, you all have 12 plus 3 minutes. Our schedule is tight, so please be on time. Me and Karin will be sharing the session, and we'll let you know when you have 5 minutes less and then 2 minutes. As I said just now, we prefer that you broadcast your slides and your image. So if there are no problems with connection, this is best. And please, if there are more questions that the time allow us, we encourage people to use the Mattermost channel, which is open. And at the end of the session today, we also let the space for speakers to continue discussions if they wish. So I think we can begin. So I invite Fabio to start. Measurements of CKM matrix elements.
Yes, hello. So you should see the slides now. So, good afternoon to everybody. Today I will report about measurement of CKM matrix elements on behalf of the LCB collaboration. So, the CKM paradigm has been tested to a very high precision by several independent measurements, as you can see from the results of the CKM FITA collaboration on the right part of the slides. And in the CKM paradigm, BDKs can be exploited in many ways. For example, CKM angles are obtained from CPV measurements, and these angles are getting more and more precise. The modulo of VTD and VTS are constrained by oscillation measurements, and the modulo of VCB and VUB are obtained from selectonic decays. And in this case, the main players have been the B factories. And regarding VCB, there has been a long-standing puzzle that I will try to summarize in the next slides. So as you can see in the right plot, there is a tension of about 3 sigma between the exclusive and the inclusive determination of VCB. And as you can see from the bands, there are several measurements, and the B factory performed lots of measurement with B0 and B minus decays. Then some years ago, there was a first step into the field by the LCB collaboration with the measurement of VUB of the modulo of VUB over VCB with lambda B decays. In this case, the measurement is affected by different systematic uncertainties and brings up independent information. So it's a very important measurement. But what I want to stress is that also B sub S decays can be exploited for the measurement of the modulo of VUB and the modulo of VCB. There is a big interplay with theory. For example, lattice QCT calculations are very promising, and will have a very good precision on B sub S form factor to extract the modulo of VCB. And I invite you to follow the next talk by Oliver. In our case, the form factor for the B sub S to D sub S mu nu are available over the few Q square spectrum, whereas the form factors of the B sub S to D sub S star mu nu are measured with a good precision only at 0 recall. Going to the LCB experiment, the experiment collected about 9 inverse femtobarns at 7, 8, and 13 TeV center of mass energy in 6 years of data taking, and we have about 10 to the 10 BSABs produced per inverse femtobarn. We have 1 kilohertz of reconstructible BSABs that are interesting for physics, and these BSABs decays are selected mainly thanks to muons by requiring thresholds on the transverse momentum and displacement from the primary vertex. And this results in hundreds of thousands of BSABs candidates that are saved on disk and are available for physics analysis. And all of this paves the way towards a measurement of BCB with the BSABs to DSABs and DSABs time in decays. So just a few words on the strategy and the data set. So the imprecise knowledge of the collected the integrated luminosity and of the PP to BBX cross section would be a limiting factor for the measurement of the modulo BCB at the order of 5 to 8% relative uncertainty. But this systematic uncertainty can be greatly reduced by using a normalization channel. And in this case, we decided to use the B0 to D mu nu and the B0 to this time mu nu, with the D reconstructed in the same visible final state as the DSABs, so is the KK pi final state. And but in this case, we need an additional ingredient, that is the ratio of the organization fractions that is called Fs over Fd, and this is measured with a precision of 5% that translates into a 2.5% uncertainty on the modulo BCB. And on the right-hand side of the slide, you can see the KK pi invariant mass spectrum. On the left side, you can see the D class with 82,000 signal candidates, and on the right side, you can see the DSABs with 272,000 signal candidates. One challenge of this analysis is to separate signal from background, and this is very hard due to a reconstructed neutrino, since we cannot reconstruct a clear BSABs peak, unlike, for example, the B factories, and thus it's very difficult to separate signal from backgrounds. But LACB already proved to be able to overcome this challenge by employing the corrected mass. The definition of the corrected mass is reported in the red rectangle in the top right corner. And you can see here, for example, one previous analysis in which the two BSABs decay channels can be separated, both between themselves and also from the physics and combinatorial backgrounds. In this case, BCBs can be obtained from a measurement of the decay rate as a function of the recoil W. But this recoil W needs to be is an approximate quantity because we have a missing neutrino in the decay chain. So the idea, the novel idea of this analysis is to exploit the perpendicular component of the momentum of this DSABs with respect to the B0 or BSABs flight direction, as you can see from the sketch. And this quantity is fully reconstructed. So is very goodly known, and is highly correlated with the W, as you can see from the bottom right plots, where you can see the true W from simulation as a function of this P perpendicular variable in a 2D-dimensional plane. And also the form factors are functions of W, so since we are sensible to W, it's also possible to measure the form factor of the decay. We need to analyze the inclusive sample of DSABs mu candidates, where the DSABs star is partially reconstructed, and we performed a two-dimensional fit to the corrected mass and the P perpendicular of the DSABs in order to determine the modulo BCB and the form factors simultaneously. And to do this, we use two-dimensional templates that are built from a simulation and that account for efficiency, for the efficiency on the two-dimensional plane. And you can see the relation between the differential observed yields and the differential decay rate that contains BCB and the form factors. We decided to constrain the form factors from lattice QCD in order to obtain, to gain precision on the modulo BCB. And the factor kappa that you see in the formula in the middle of the slides contains the measured B0 reference yields, the input branching fractions, the ratio of the transition fractions Fs over Fd, and the B sub S lifetime. Going to the results, so we needed to choose a form factor parameterization in order to determine VCB, and the first choice was a general model from Boyd, Greenstein, and Lebet, that is commonly called BGL. And here you can see the results for the model of VCB and the two fit projections on the left for the corrected mass and on the right for the perpendicular momentum. And you can see that the fit quality is pretty good, and we have a p-value of 63%. Then we also performed analysis using a different form factor parameterization. In particular, we decided to use the Caprini, Leluk, and Neubert parameterization that is called CLN. But as you can see from the projections in the two bottom plots, the one on the left is for the B sub S to D sub S mu, and the one on the right is for the B sub S to D sub S star mu. You can see that the fit results and the data compared between CLN and BGL, they are almost identical, so that there are no significant difference found between the two parameterizations. For the measurement, the dominant uncertainty is due to external inputs and is a 3% relative on the model of VCB, and this is mostly due to Fs over Fd. And the second one, dominant uncertainty, is the knowledge of the D and D sub S KK pi die structure that brings up 2% relative uncertainty on VCB. Some additional results of the analysis are the first measurement of the exclusive branching ratio that you can see here, and also the ratio of the two exclusive branching ratios. And these results are compatible within 0.1 and 0.7 sigma with precision from Bordone, Gubernari, Van Dijk, and Yang. Now I go to another complementary measurement, that is the shape of the B sub S to D sub S star mu differential decay rate. This measurement is performed on a completely independent data set, and the main challenge in this case is to reconstruct the photon in D sub S star to D sub S gamma decays in a cone that is around the D sub S flight direction. And then one performs a fit to the D sub S gamma invariant mass in order to subtract the background that is due to random photons in the vents. And on the right part, on the right plot, you can see the results of this fit. Then one needs to approximate the W by employing some MVA-based algorithm and fit the correct mass in beams of the approximate W in order to obtain the differential decay rate. And on the right part of the slide, you can see two fit projections for two different beams of W. You can see that in these cases, the main backgrounds are due to the B sub S to D sub S star tau nu decay and to this B sub S to DS1 2460 mu decay. The result for the analysis can be obtained once one unfolds the efficiency and the resolution by using simulated events. And then one can fit the differential decay rate with both the CLN and the BGL parameterization, and you can see the results of this fit in the top right plot. And also another important thing to notice is that this analysis shows a good agreement with the form factors that are measured in the analysis that I presented before, so the VCB analysis, that are represented as shaded histograms in the bottom right plot. So, coming to my conclusions, the LCB collaboration proved that B sub S to the DS mu and B sub S to the S star mu decays are a viable option to measure the form factors and the model of VCB. In particular, today I presented a first measurement of the shape of the B sub S to the S star mu differential decay rate, and the first measurement of the model of VCB at the Hadron Collider using B sub S to the S mu and B sub S to the S star mu decays. And in the red box, you can see the results obtained in the two different parameterizations, the CLN and the BGL parameterization. And those results that we obtain are in agreement with both the exclusive and the inclusive determinations, as you can see from the right plot that collects all the measurements, exclusive measurement of VCB performed in the last 20 years. And that's all from my side. Thank you.
Thank you, Fabio. Questions for Fabio? You can raise hands or just jump in. Yes, Doris, go ahead.
Can you go back to page 14? where we show the distribution of over recoil. Yes, 15. Sorry, I was talking about. Yeah, okay. It doesn't matter. Yeah. I was wondering how whether the lattice people will give you a distribution similar to these plots.
Sorry,
lattice QCD. Lattice QCD.
So when we will get a prediction from lattice QCD on this, is that?
Yeah, in this recoil variable.
I'm not sure that on the timeline of this, or if we already have a prediction on this. Actually, I'm not sure. We have prediction for sure on the form factors that we have. And by comparing them with predictions, they agree pretty well. But we have also to say that the uncertainties are pretty big at this stage, so it's not a very precise step. But the prediction from for factors, they agree with the LACD results. That I can tell you.
Okay, thank you.
Okay, we can go to the next question. Someone, oh yes, Christoph.
Yes, can you hear me? So I have a similar question. This measurement of BS to DS mu, does it cover the whole Q square or W range, or is your sensitivity concentrated in a particular range, and does it match the lattice prediction? Do you have a good overlap, or do you have to make an assumption to connect the both?
So you are referring to this spectra in Q square?
Yes, exactly.
Okay. So as far as I know, the W range is from 1 to 1.5 approximately, and this can be translated directly to Q square. So I would say yes, this is a measurement of the full spectrum of Q square that you can have. Yes.
And the latest prediction is also over the full range, or is it only in a particular?
For the B sub S to D sub S star mu, I am not sure if we have lattice prediction just at zero recoil, that is Q square equal to 0,
okay.
or on the full spectrum. Probably Oliver in the next talk can be more precise than me, but I'm not completely sure on this.
Thank you.
No problem.
Okay, thanks, Fabio. Again, we can move on. The next talk is from Oliver Witzel on non-perturbative calculations of form factors for exclusive semi-leptonic B sub S decays.
Okay. Can you see my screen?
Yes.
Okay. So sunny greetings from Colorado, and thank you, Fabio, for the nice introduction. So I will continue talking about B sub S decays, but from the lattice perspective to calculate the non-perturbative contributions. And first of all, I would like to thank my collaborators on this project, in particular, Jonathan Flynn, Brian Hill, Andreas Jüttner, Edwin Lizarazu, Amjad Soni, and Tobias Zhang. So as you all know, we are interested in determining fundamental parameters of the standard model, like the CKM matrix elements. We are also interested in addressing observations or challenging the standard model, which are interesting. So in particular, the Lepton Flavour universality tests and the ratios RD and RD star have caught a lot of attention recently. And so far, we are looking at this typically for semi-leptonic B decays, but we can also look at that for B sub S decays. And as we just learned, LHCb can do a wonderful job in measuring these decays. And so we get an independent cross-check on the commonly used channels B2 pi L nu and B2 D star L nu if we look at BS to DS L nu and BS to K L nu, for example. Since we are only exchanging the spectator quark, flavor symmetry should hold very well. And we expect that this is really a good cross-check on what we have. And we can also hope to address these long-standing discrepancies between exclusive and inclusive determinations. Likely, looking at B sub S decays will be more precise than B2 tau nu decays. And it's a further alternative is to look at the baryonic decays of a lambda B going to a proton. From the lattice point of view, looking at strange quarks is definitely favorable because they are making the lattice calculations easier. Now, basically a one-page summary of the lattice calculations. We work in Euclidean time. So we do a Wick rotation and discretize space-time to a rectangular grid. And then we can turn the path integral into a large but finite dimensional job, which we can tackle with statistical methods. However, we do have the length of the box as an infrared regulator. And at the same time, the lattice spacing works as a UV regulator. So we have to obey constraints that the light quarks are happy, not feeling too squeezed in the small box, but at the same time, we do need to have high enough resolution to deal properly with the heavy quarks, in particular with the bottom quark, and the general rule of thumb is that the quark mass in lattice units needs to be less than 1. So depending on the lattice spacing, whether it's coarse or more fine, we have different concepts on how to deal with the charm and bottom quarks. And while for the bottom quarks, I'm going to refer to a relativistic action in this work. We are using a fully relativistic action for the charm quarks in the B sub S to ds decays. Now let me jump right away to the first decay. So looking at BS going to KL nu, and the process is sketched here. So we have the strange quark, which just goes unchanged. And then we have the bottom quark, which on the left forms our B sub S state, and it decays under the exchange of a W to a U quark and forms the kaon. The W itself will give us a lepton-neutrino pair. So this is the charge current decay, tree level in the standard model, and the experiment will determine the branching fractions, and then we can parameterize that in terms of known coefficients, plus the CKM matrix elements highlighted in blue, VUB. And in addition, we need to have the form factors F plus and F naught, which are the non-perturbative inputs. So they parameterize the contribution due to the strong force. And we use an operator product expansion to identify the short distance contributions. And these we can calculate on the lattice by determining matrix elements for the flavor changing currents, and that's basically a point-like operator. Schematically, this is then how we really enter the lattice calculation. So we want to calculate this matrix element, a BS, changes under the vector current to a kaon. That can be parameterized by the two form factors we defined earlier. And in the picture, it's shown as we have a source on the time slice T0. We let the strange quark propagate in time to a time later T sync. At that point, we create a so-called sequential source for the B quark, which goes then back in time and is contracted with a light quark also originating from T0. And at this point here, we have the operator insertion and vary the range between T0 and T sync to determine the signal of the 3-point function. Now on the lattice, we are having discrete symmetries. So instead of directly computing F plus and F naught, we prefer to compute F parallel and F perpendicular, which are then just the temporal and the spatial directions in the 3-point function. And both are, however, linearly related to F0 and F plus by forming the appropriate combinations given on the bottom. And to give you a picture how this looks like, this is an example for our finest ensemble. In this case, the B meson is on the right, the kaon is on the left. The blue data points are the signal we are observing, and then we are looking for the flat range in between. And on the left, this is F parallel at 0 momentum, and on the right, it is at 1 unit of momentum. And we then look for the flat range, and we can account for so-called excited states contributing. So you see a little bit of curvature. It's better resolved on the left, where we account for these additional states in the fit function to determine the plateau. And what is shown on the left here are how the two determinations of just fitting the ground states or including excited states perfectly agree, which gives us a handle on the systematic of the signal we are determining. Now we have to do this exercise for all the ensembles we are using. And for different momenta. So what you see here are now a set of 6 different ensembles. Each ensemble is given by the same color and is statistically independent. The red colors refer to the coarsest ensemble, the blue ones to the medium ensemble, and the green one is our finest ensemble. So we have 3 lattice spacings. And then we have on the coarse and the fine different values of the light C quark mass, which gives us a handle on how to estimate the effects due to having unphysical heavy pions in the C at this point. What you see is that we could determine the values for different momenta of the kaon, and these data points of the same color are now correlated. So what we do is, to obtain a chiral continuum limit, we fit all of these data points together using an ansatz inspired by heavy meson-chiral perturbation theory given on the bottom. And then we obtain the colored lines, which are supposed to pass through the same colored data points. And in addition, the chiral continuum limit, where we are extrapolating all quark masses to their physical value, and the lattice spacing is sent to 0. That is the black line with the gray arrow band. And this covers the range where we have data in our simulation directly. And on the left, this is the result for F+, and on the right, it is for F0. Now, once you have done that, this result only shows the statistical uncertainty on the chiral continuum limit, but we now have to estimate all sorts of systematic errors, and I have a long list here. And instead of going through this list in detail, let me just show you a few plots. First of all, we need to address the systematics due to our fit ansatz, and this is done by doing variations. And in these plots, you see the gray background is our preferred result with a statistical uncertainty. And then the colored lines give us different systematic effects from varying the fit function by omitting terms or by changing the pole term and so on. And basically what we see is that everything is on the same order as our statistical precision for F+, whereas there is one uncertainty which is relatively independent of Q square, which is a little bit larger for the higher Q squares in case of F0. Now, in addition, we have to estimate the uncertainties, which we cannot get from just varying the fit function. We need to look at discretization effects and uncertainties of the input parameters, etc. And this gives you then the layer plot where the statistical error is on top. The systematic due to the fit is given in blue, and the other uncertainties are then color-coded on the bottom. All in all, we get a result of around 4% for both form factors in the range where we have Q square. Now, as Christoph was asking in the last question, this is a restricted range in Q squared, which we are studying, and we want to extrapolate that over the full range. And for that, we need to refer to the kinematical extrapolation or Z expansion, going back to Boyd, Brinstein, and Lebet, and later refined from Borelli, Caprini, Lelouch. And it is basically mapping the Q square plane with a cut onto the unit disk in Z space. And this is the equation you do. The basic philosophy is that you are converting the parameter range from Q squared to a well-defined range on the unit disk, and you symmetrize the fit range to improve the kinematic extrapolation. And so you can just go forth and back between Q square and Z. It's just easier to perform the expansion in the Z parameterization space. Specifically, we are using BCL right now for testing out our fits. So the equation is given up here, and then we need to account for the product of factors for subthreshold poles in the case of BS2K. This is now a first look at our BS2K expansion over the full Q square range. And since I'm running out of time, I can just show you a quick comparison to other lattice results. And all in all, there is good agreement with this still persisting discrepancy at 0 Q squared to the HBQCD 14 result. But we are still working on making the comparison here. We're also working on including analytic predictions. So in the last minute, let me quickly jump to BS to DS, which basically has the same equation, except that we have to deal with the charm quarks here. And this is the status of our result. We have the chiral continuum limit implemented, and we have a good result here. And there you can see that the range in Q square is significantly smaller because the ds is eating up much more of the energy. And what we are doing here is either an extrapolation or a small interpolation to the physical ds meson mass. Now we are still working on estimating the full error budget. And what we already see, it is a harder task because the statistical errors are significantly lower. They are of the order of 1%. So you have to be more careful in considering all the systematics because they can be more easily be significant. And at this point, we hope to have a final result of a few percent, but that is still under heavy discussion within the collaboration. So let me briefly summarize. The calculation for BS to KL nu is essentially complete, and we are working on the comparisons and extracting phenomenologically interesting quantities. Whereas for BS to DSL nu decays, we are still finalizing the systematics, but we are hopeful to finish the result very soon now. Thank you.
Thank you, Oliver. We have time for one question maybe, and we encourage people to make questions at the mattermost too. So any question? Okay, so I see no raising hands. So thank you, Oliver, again. We can move on to Russia. First results on VUB and VCB with Bell 2.
Okay, should I share my screen?
Sure.
All right. Okay. All right. So I don't know how to get rid of the Zoom, but anyways, so this is a talk on the first results on VUB and VCB with the Bell 2 experiment. So the Bell 2 experiment, brief intro, it's a B meson factory in Tsukuba, Japan. We collide electrons and positrons at an asymmetric energy, and we produce B meson pairs primarily. It's an upgrade of Bell 2 to higher luminosities. Our target is to collect 50 times the Bell 2 dataset. This will give us a large number of B, charm, and tau events, and these will therefore allow for a very rich physics program in determining, like studying B anomalies, looking at Lepton Flavour violation, or studying charm mixing. So our current Bell 2 data set, we recently started data taking. Our current data set is around 74 inverse femtobarns. For today, our results are presented with our 34.6 inverse femtobarns of reprocessed data. So VCB and VUB, as presented by Fabio, precision measurements of the CKM matrix elements are at the core of the Bell 2 physics program. We're a flavor factory, and so we plan to determine these elements precisely. And for VUB and VCB, these are determined primarily from semi-leptonic decays of B mesons. And you could see here there's this tension between exclusive and inclusive VUB and VCB measurements, which we want to investigate and measure along with other related B anomalies. And so for inclusive decays, there are a couple of ways to target these. So inclusively is where we don't fully reconstruct the X system, which is seen, and then exclusively is where we fully reconstruct the decays of the B meson in the semi-leptonic decay. And we could also use tagged measurements where we reconstruct also the other B in the event along with the signal B. So here today I'll present where we're at in terms of measurements of VCB and VUB at Bell 2. So to start with, one of the modes we've looked at is this exclusive B to D star LNU decay. Here, this is an untagged measurement. We exclusively reconstruct one of the we don't exclusively reconstruct one of the B's in the event. We exclusively reconstruct the B to D star LNU signal decay. This is the flagship decay for VCB measurements. To determine this, we reconstruct D to K pi, and then the D star is reconstructed by combining it with a D and a pion. The lepton is identified using a PID algorithm, and we express continuum events by requiring that the D star momentum should be less than 2.4 GeV and by cutting on the Fox-Wolfram moment. Here you see a plot of cos theta By in both the electron and muon channels, and you could here where cos theta By is the angle between the B and the Y is the system made up of the D star and the lepton in the center of mass frame. So for signal events, we expect the cos theta By to range between -1 and 1, and we see this clearly in our two plots. We extract the signal using a fit to this cos theta By distribution, and we find that our branching fraction is compatible with the current world average. We also look at the ratio of the D star E nu to the D star mu nu modes. And moving on, we also examine the hadronic recoil parameter spectrum, W, defined here in the top left corner. What we do is we divide our spectrum into 5 equal bins of 0.1008. Here you see a plot on the top center, a plot of W for the full spectrum. And we also see for the muon modes, D star mu nu entries in the first W bin. Determining these partial branching fractions in bins of W are a key step to actually determine VCB. And so we see here we have a good agreement between our expectation and data. So this is a good milestone for further precision measurements here. We also unfold the W spectrum to compare with theoretical distributions. So we unfold the spectrum and remove reconstruction and resolution effects. And we do a first comparison in these 5 bins with the BGL theoretical predictions in the partial decay rates that's shown here, and we see general good agreement. And so in the future, we plan to determine these partial branching fractions of VCB and perform further comparisons with more and more data for higher precision. So another important decay is the B to D LNU, where here we also exclusively reconstruct the decay products as D to K pi. In addition, this is very similar to the previous D star LNU results just presented, but in addition, we apply a D star veto by combining the D candidate with any soft pion or any soft pi 0 or gamma, and see whether we get a mass D star candidate with a mass compatible with the D star mass. And you can see here in the yellow, the D star crossfeed is important in this mode as expected, but we see good agreement in data in Monte Carlo. And this is also the first measurement of this mode in both the electron and muon mode, and more precise results will follow in the near future. So moving on to inclusive B to X LNU decays, we start with B to X U ENU. So this is a flagship decay for measurement of inclusive VUB. Here we don't fully reconstruct this X system, and to determine VUB, what we do is we look in for in a BB bar event, we look for a lepton. And we look in the endpoint spectrum of the center mass momentum. So that endpoint spectrum is defined between 2.1 and 2.8 GeV. And to look for these events, we identify one lepton using PID algorithms. We suppress continuum events using a multivariate trained on event shape variables, and we use off-resonance data to estimate our continuum contributions. We use simulated Monte Carlo in sideband regions, so not in the endpoint below 2.1 GeV to fit other BB bar contributions. And then we subtract these from the endpoint spectrum and look for excess. And here you could see an excess in B to X ENU in data. And this excess is equivalent to, is greater than 3 sigma. So moving on, we now look at tagged decays, and by tagged is here we use hedronic tagging, where we fully exclusively reconstruct one of the B tags, one of the B's in the decay using hedronic modes, and then look in the rest of the event for our signal B. This allows us to infer the momentum of our signal B and is ideal for decays where we have missing energy, because any missing energy in the event can be attributed to the signal B. We here for these analyses, we're using this full event interpretation, which is a novel technique developed at Bell for Bell 2. See the talk by William Sutcliffe on Thursday, but this is this tagging algorithm has almost twice the efficiency at the same purity for similar techniques. So using this tagging, we also measure B to pi L nu, which is another flagship decay for VUB exclusive determination. Here we reconstruct the hedronic tag and then look for pion and lepton. And then we reconstruct this missing momentum vector and look at the missing mass square distribution shown here. The signal region is defined in the missing mass squared region below 1 GeV. We extract the signal using a fit in that signal region, and we find a branching fraction of 1.58 times 10 to the minus 4, which is in agreement with world average. And our current significance is around 5.7 sigma. We also, using our tagging technique, look at the exclusive B to D star L nu decay. And here we construct D star to D pi, D to K pi. We identify this high momentum lepton, and we also look at this missing mass square distribution and extract the signal yield using a fit to this distribution. Our current result is in agreement with the world average, and we see good agreement between our data and Monte Carlo expectations. So, and finally, using our tagging, we also look at the hedronic mass moments, which are one of the targets, one of the goals in our with Bell 2 to determine these hedronic mass moments. These are used to determine BCB and the mass of the B quark. To do this, we use FEI hedronic tagging, but we infer this X sub C system using whatever is left over in the event, so the rest of the event after reconstructing the tag B and the lepton. This is our X sub C spectrum shown here. We subtract backgrounds. The backgrounds are shown on the right-hand side by assigning a signal probability to each event, and these backgrounds are estimated using 2 control samples where we have the signal B and the lepton have the same sign. And once we subtract our backgrounds, we extract our moments. We first determine these calibration moment functions to correct for any experimental and resolution effects. And we have an additional factor to correct for calibration and reconstruction bias. And we extract the first 6 moments in the B to XCL nu. Here we show our moments in comparison with previous experiments, the Bobar and Bell specifically, and we see reasonable agreement given good agreement with our statistics. So towards higher luminosities, we have the platform. I guess we're building up our measurements with more data. We expect to reach higher precisions and better understanding of detector performance. We expect to decrease our uncertainties on VUB and BCB, both exclusive and inclusive measurements. These uncertainties will be decreased by a factor of 2 or more, depending on the mode. So in conclusion, we've shown first measurements for both the tagged and untagged B to D star L nu at the Bell 2 experiment. We also did the first measurement of beta pi L nu and showed evidence of non-zero VUB in the lepton momentum endpoint. And we also performed the first measurement of the hadronic moments for inclusive beta XC L nu. There will be more to come with increased luminosity. Thanks.
Thank you, Rasha. Very exciting to see results from Bell 2. Are there questions? Okay. Please, as I said before, please use the Mattermost for any questions that may appear. Well, thank you. And now I pass the baton to Karim.
Hello, thanks. Okay, so there are still 2 talks before the coffee break. So I propose we go on with Franco Simonetto about the angular analysis of the B2D and D star lepton neutrino decays at Barbara.
Okay, can you hear me, please?
Yes.
I'm trying to share my screen. There we are, there we should be. Can you see my slides?
Yes.
Okay, very nice. So I thank you for inviting me to have this talk. We pass from a brand new experiment to a very old one, which stopped running several years ago, but is still producing results. And here I'm going to present a measurement of form factors in B2D star lepton neutrino decays. So the reason for that, well, it's pretty clear to all the people in this audience. We have many long-standing issues in heavy flavor physics. Among these, the poor or completely wrecked compatibility between the determination of BCB from inclusive and from exclusive decays, which might either be a sign of some problems in our understanding of the decay processes which bring to these final states, or maybe could even be a hint that there's new physics in the form factors which describe the decays. Let me briefly remind the game of rules. By one side, this is a measurement which exploits a deep interplay between theory and experiments, because the role of theory is to convert from the very beautiful, ideal, and easy life at the quark level world to the hard reality of the observed hadrons. Then the role of the experiments is, of course, to compute rates and branching fractions, but in addition to that, they can provide constraints to the theory by measuring spectral shapes, differential rate, and particularly form factor, as is the case for this talk here. So, you have already seen this formula before. You know that we can decompose the partial decay rate in terms of, well-known parameters as the Fermi constant, then some electroweak correction, BCB, which is the name of the game, then phase space factors, and a term which is connected to the helicity amplitudes which describe the decay, which can be also formulated in terms of 3 form factors, 1 vector, and 2 axial vector. And in fact, they can be measured, or I should say more correctly, constrained to a 4-dimensional fit to, well, the Q squared, the square of the momentum carried by the W meson, and then 3 helicity angle, which parameterize in detail the details of the decay of the W and of the D star. Due to the limited data size, however, you cannot really determine the shapes of form factor just from the measured spectra, but you need some input from theory, and then you can interpolate the theory prediction determining a few free parameters. So the first step in determining form factors is redefining the variables in such a way that they are easier to be dealt with. So we move from Q squared to the omega, which is in fact V times V, and which is related to Q squared in this way. Then omega can be mapped to another variable Z, which has the quite pretty feature of being contained in a very small region. So, so perturbative expansions can be done in this parameter. And that's what, for instance, done with the parameterization of Voigt-Greenstein-Lebed, which express the form factors in a power series expansion with a really minimal theoretical assumption. This formula is very well known. And you see basically that can express the form factors in terms of well-known functions, and then a power series in Z, which depends on few unknown parameters that are this AI. Well, they are free parameters, but they have an analyticity bound which limits their maximum possible values. So already should be a small. So the sum of AI must be less than 1. Okay, so in practice, then for this measurement, we will not push the development to infinity, stop at n1 equal to 1 due to statistical limitations. An alternative approach has been proposed by Caprini, Lelouch, and Neubert. This is a bit more aggressive than the other one in the sense that it uses HQET bounds to reduce the number of free parameters so that we have this expression for the form factor, the one of the actual form factor, which is expressed in terms of a normalization term produced by lattice QCD and the slope. And then we have the other two form factors that are expressed as ratios to the first one, and the only free parameters are the normalization of the two ratios. So basically, with this approach, you only need to fit a slope and two normalization parameters. Coming now to the measurement, we have seen in the previous nice talk what I would like to call an old approach, the first approach that all experiments has been following since the time of Clio and Lep. And basically, you select an untagged sample, which provides you a large data set. However, with a sizable background, with a coarse resolution because you missed the neutrino. And up to now, all experiments didn't perform a full fit, but they fitted to 1D projection and then take it into account correlation to get the result. What I'm showing here now instead is a new approach based only on peaked event, which gives, however, a small data set, but as we will see with the algebraic background, with a terrific resolution in each of the parameters due to kinematic bounds, which allow these two facts allow to a full fit to the 4D space. So it's a tagged analysis. So we have a tag side and the signal side. The tag side consists, as we've seen before, in fully reconstructed, that don't be the case. We use 10,000 modes, more or less, which gives a very loose selection with high efficiency and low purity. But we don't care about the low purity because the signal side is pretty clear. We have a fully reconstructed semi-leptonic decay where only the neutrino is missing. So in the end, we have very clean data sets. So as for the selection, I wish to underline that we have a very constrained system because we know everything about the two, every fully reconstructed one of the bees. We know everything about the other, then we have mass constrained. So it's an over constrained system, which allows us, for instance, to reconstruct both the energy and the momentum of the missing neutrino and compare the two of them. And so you see what's the resolution that we get when we make the difference between the missing energy and missing momentum. It's of the order, sorry, I wrote, yes, the full width maximum of this distribution is about 50 MeV, which is quite a score for neutrino reconstruction. In addition to that, you can use the confidence level of your overall fit in order to further decrease the background, and then we also have a light cut on the extra energy carried away by low energy photons. All in all, as you can see by inspecting these plots, which contain all the cuts apart those for the variable we are looking at, you see that we have a wonderful signal to noise ratio. Background is below 3%, which is quite a score for semi-leptonic measurements. So as fits, we perform a couple of them and not extended mean maximum likelihood in order to determine just the shape parameters. Or in addition, we also perform an extended ambient maximum likelihood where, however, we feed our fit with information from outside. In fact, we ask that our integrated rate be equal to the ratio of the branching ratio and the lifetimes of the B involved as provided by the ICHEP working group. So first, before coming to results, I show you the fit quality. It's not easy to compare, but on top, you have the data distribution for the chi versus cos theta v and integrated along Q square in 3 bins of cos theta L. So this is an attempt to make a full description of all the variables employed in the fit. On bottom, you have the output of our Monte Carlo reweighted to the fit results with input parameters corresponding to the fit results, and you should try a 2D comparison of the two plots. If your eyes are not well trained on that, you can look at the chi-square over n bins, which is coming out from each of these 3 plots, to say that all in all, we have quite a good agreement. So coming to the results, here I have on top, you see the results for the Boyd et al. Parameterization. On bottom, you see the results for the Caprini, Lelouch, Neubert. Well, these numbers are not going to tell you much. The value of VCB, you can see it's quite consistent with the one you have already seen in the past. The overall error, which includes statistics and experimental systematics, is small, but not as small as in other cases because of statistical limitation. What is worth to underline, however, is that you should look in the 3 plots where we show the form factors in the Caprini parameterization. You can compare the blue line to the red one, showing that these are our experimental results, and they simply confirm that our data are both consistent with both parameterization. Boyd and Caprini provide a similar result, even if they have different structure. What is more striking is the comparison of the blue line with the green line, because the blue line is our result, which I remind you is much less dependent, for instance, on background, and is driven by a much better resolution, with the world average, which is the green line you see here. And you can appreciate that in all the 3 cases, the two curves don't match well. And this is particularly true if you look at the second actual vector form factor, where the difference between our fit and the world average is quite striking. If we perform an overall comparison of our results with those published by ICHEP, we see that compatibility, the p-value is less than 2 per mil. So coming to conclusion, I have shown you a new approach to make a very old measurement nowadays, which I'm sure is paving the way for future measurement of VCB and form factor, thanks to the fact that it has negligible background and excellent resolution. The most striking result of this analysis is that the shape of form factors is not consistent with what is tabled from a previous measurement, even if apparently this is not explaining the difference between inclusive and exclusive results on VCB. So clearly Babar is over for this game, but we have just heard that BEL2 is entering the game. And so we can be pretty confident that quite soon, if BEL2 will apply this same technique to the huge amount of data that they are going to collect, we will probably solve all present tradition, or at least hopefully, and maybe be able also to release theory constraint in order to provide a less model dependent determination. Okay, with this I'm over, and I thank you.
Thank you. I think we have time for one question. I see already, well, okay, I see two. If let's see if they are quick enough. So Christoph.
Yes, I hope it will be quick. So I'm a bit puzzled by your claim that your shape that you measure is not consistent with the world average. Because in principle, you use the world average d*nu branching fraction. To get a value of VCB, you must extrapolate to the zero recoil point, and the result is consistent with the world average. So if your shape would be inconsistent with the world average, how can you get a consistent value of VCB? So that doesn't seem to...
Well, first of all, you should notice that the main discrepancy is coming from one of the three form factors. And you remember that the parameters that we are fitting is the normalization of one of the form factors to the other one. If I don't know if I have in the yeah, here I have. You can maybe appreciate the fact that the main discrepancy we have from the world average is in fact on the normalization of the second form factor. You can also see that the slope is not very different. Slopes are quite consistent, but the normalization of the second form factor is quite different. So here is that where we have the problem. Apparently, however, this is, it's very difficult going from one projection to a four-dimensional adjustment. Apparently, this is not affecting the overall rate, but just the shape on one, just the normalization of one of the form factors.
Okay, thanks.
Okay, if the other question is much faster, then I would also take the other.
Yeah, so this is following up essentially from the previous question, so it can be very fast. So I want just to notice that the actual ICHEP combination for these measurements has a pretty poor consistency, has a pretty poor p-value. So I wonder whether the discrepancy is with any of the specific measurements that enters the combination, or I mean, if you looked into a little bit more details and not just at the overall combination, but even at the individual measurements, there are a bunch of measurements by Babar and Bell that enter the determination of this world average.
Okay, of course, sorry, I cannot answer to your question, but I take the point and we will make a comparison. I could also just go through the parameters measured by all other collaborations and let you know the answer in not a long time.
Okay, thanks a lot. So for any further discussion, please use the Mattermost channel. Now I would say we go on with the last talk before the coffee break. Marcella Bona, who will discuss about the updates on the unitarity triangle by the UT-FIT.
I need to share. Hello, everybody.
Hello.
Okay.
Okay, you can start.
Thank you. Okay, so I'll give you the usual update on our fits with the UTFit collaboration. So I've updated the analysis with new inputs. So every single plot and single number is updated with what I label the summer 2020 inputs. And I'll go through the standard model analysis and the new physics analysis with the different properties and interests. So this is just a reminder of our website. As the plots and numbers, as I said, they are really just hot off the press for this conference. So they are not on the website yet. I expect I need to do a little bit more statistics, but in general, they will appear in the next days. Again, I'll just remind you what we use. We use the variation approach, and we need to have the observables. We need to have the connection, the functional connection with the theoretical parameters, and then we need some parameters that allows us to go from the hadron level to the Quark level that we are operating at. Okay. So we have heard already a lot, so that's good that I included this slide. So we have our own, so from our point of view, we try to use VCB and VUB as inputs. And of course, as you know, there is a little bit of a discrepancy. So these are the latest numbers that we could cook up a little bit. So the exclusive numbers both from VUB and VCB are from FLAG. That was the latest updates that we got. And then the inclusive results are from HFLAV, but you see that for the VUB, we noticed that there was a spread in the central values, and so we took a flat error to cover that given spread. The other thing, so in the plot, you see the various visualization of these numbers and their errors. And they usually, so we heard about LACB and their measurements of VUB over VCB. We have nothing against LACB and this measurement. However, we follow the flat guidelines, and because the lattice numbers are coming from a single collaboration, they're not included in our average. So regrettably, we took it out from our average. However, what we did is also to do a PDG inflation, a la PDG inflation of the averages. So you see that the blob, the orange and yellow blob of the UTFit average in the plot is really covering all possible intersection of the inputs. And basically, these are the numbers that we get with this procedure on this page. At the bottom, you see also the comparison with the UTFit prediction that, I call them prediction when I run my fit and then I remove the inputs that I'm interested in looking at. So this is what the numbers that fit prefers without using VCB or VUB respectively. So then the other game we do is run the full fit to separating the exclusive and inclusive values. So I ran this with VUB and VCB only exclusive on one side and only inclusive on the other side. Now the fit is becoming very precise, so I need to zoom in. And then this is the zoomed in version. And you see there is a little bit of confusion, especially in the exclusive part, where there is a little bit, there are tensions, especially with epsilon K. I report here the tension that we see with sine 2 beta, which is the usual way we look at this type of tension, and that we are at the 2.3 sigma level. So then the other update we did is the latticity inputs. There's been some updates and also some different choices in calculating the average by our lattice colleagues. I don't have too much to say on this. just to make sure that we that people know what we're using as input. There's a little bit, so most of the results are similar to our past update. Because of this different way of calculating the error has gone down a little bit in the first 3 lines. So the BK and the FBS, and then the ratio, the BSBD. Okay, so that's a little bit the effect that we're seeing with respect to our last update. And then we put everything together. This is just the summary of the main constraints, and we get to the full standard model picture. And with this number, again, it's getting hard to see the area, so I zoom in. And this is showing quite a nice agreement. And of course, you can clearly see that partially this nice agreement comes from this a little bit bigger band from the VUB, VCB, the yellow band that you see there. And that's clearly one effect that we can see. Now, then what we can do several configurations. So I chose the classic ones that we've been looking at. And so at the top left, you have the universal, the Burras universal unitary triangle. And then the bottom left, the tree only case, where you only use three level processes. So gamma and BUB over BCD. And you see there, for those, I also put the values for rho and eta with a little bit increased uncertainty with respect to the full fit, clearly. And then on the right, you see the case of the angles only and the size. Again, it's good to zoom in. So I did the same for, in this slide, you have exactly the same structure as the previous one, but it's just zooming so that we can actually see the area that is selected by the fit. The other way we have to look at how the inputs are compatible with each other is this compatibility plot. And basically we run the fit without the observable that we're interested in. And then we plot on a 2-dimensional plane, the observable and its error. And then the experimental value that we usually use as the input will become just a point in this grid. And that's what you see here. And this is the case of alpha and gamma, where we have rather good agreement at the level of 1.1 sigma. If you go next, we usually then check the usual tension that we expect in a way. And so there is VUB, as I've already mentioned several times. Here you have the cross is the input value that we use, and as I already mentioned, it has an inflated error, so you have no tension there. But then if you split into the exclusive or inclusive values, you see that the inclusive is the one that less agree with the rest of the fit, as we already know. On the right, you have the sine to beta, and again, we have a 1.8 effect from sigma effect from of tension with the fit. This slide shows a summary of all this, and you have again the measurement as the inputs that we use, and also the prediction that comes from the fit without using the given input. And then the last one, the sigma of agreement is somewhat. And then again, you have the arrow is not matching. But anyway, you see that 2.3 from the UB inclusive, and then the 1.8 of sine to beta are the main highlights here. Then the other things that we can do, we can revert our fit, not really reverse, just add extra observable. And basically saying, because we are over constraining at the moment, because we have a distance amount of constraints, we can even push it a little bit more and add extra constraints that represents new physics spaces. So for example, we can imagine to have an amplitude from new physics and a phase coming from new physics. And that's the most generic parameterization. And that means, though, that you need to reinterpret your observable in line with this extra amplitude and phase. And you see how we reinterpret the standard constraints at the bottom of the page. And then we can look at these new physics parameters two ways, either as a multiplicative factor to the amplitude, or you can also look at the ratio between the new physics over the standard model amplitude. So to do this, we are also helped by new other constraints that are not particularly useful in the standard model 1, but they are useful to constrain also the B sub S sector, and also to have constraints that act on both the size and the phase of the new physics that we implemented. And so this is typical, for example, the semi-electronic asymmetries are giving you this kind of constraints. At the bottom of the page, I mentioned phi s. Now, we had different type of inputs, but at the moment for our analysis, we use only phi s. And so we don't use also delta gamma s at the moment. And so basically, we did a UT-fit style plot with the current situation. And if you project on the x-axis, so you look at from the point of view of phi s, the measurements are not particularly in tension. And so we can do a simple average, which is the gray blob that you have there. Of course, if you want to use delta gamma s, then you need to think a little bit about it, and that's what we're gonna do in the next month. Because clearly there is some discrepancy, or maybe the LAC will look into that as well. So then we run the new physics analysis and the fit, and we get out the usual rho and eta values, and this is the rho and eta plane where we plot only the constraints that are unaffected by new physics, so the 3-level constraints basically. And you see that the errors on here are a little bit bigger because, of course, you have added degrees of freedom to your fit. But then you can also look at the new physics parameters as I implemented them. And here you have on the left side, the B sub D system, and the right side, the B sub S system. And then you see that there is the area allowed for these new physics parameters, and also the red cross is the standard model. So you can see how there is a little bit of tension, in particular in the phases, not too much in the amplitudes. Another way to look at this is judging the amount of new physics amplitude still available with respect to the standard model that the fit can accommodate. And here you have so this ratio on the x-axis, and then again the phase on the y-axis. And basically you see that these sub-axes, we saw that the errors are reducing, so it becomes quite constraining of your new physics space. But still, you still have 25–35% of new physics that is still possible in this scenario, in the current scenario. Now, the last thing that we usually do is to reverse, again, in the new physics scenario, to switch on all the operators that can appear once you have new physics. And there, the new physics effects are coded in the Wilson coefficient. And then the Wilson coefficient can be then be interpreted as if as made of 3 factors coming from the flavor coupling of the new physics, a loop factor that is how the new physics coupled with the standard model, and then the lambda, which is we call the new physics scale, but it's basically, you can imagine there is a mass of the new particle mediating the delta effect equal to 2 processes. And then you can revert your constraint. You get the constraint from the fit and the Wilson coefficient, and then making different assumptions in different scenarios, you can extract a constraint on lambda. And that's what we want to do. If you don't have new physics effect, you get a bound, a lower bound on the new physics scale lambda. And of course, you can choose different type of couplings, or flavor couplings that are standard model-like or not, or generic, and then different type of couplings of new physics with the standard model. Now, the default we take is as one, so a strongly coupled new physics with standard model, although it's unrealistic, but it's not important because whatever result you get, then you can just scale it with the coupling that you want. And so this is the result for the Wilson coefficient and the new physics scale, really. And the different colors are the different Newton-Meldon systems. And so the stronger one is usually chaos, and it's still the case with this updated results. On the left, you have the generic scenario where you have a generic flavor structure. On the right, you have an extra flavor violation scenario where you have basically a CKM structure with arbitrary phase. And this is and the limits on the lambda, of course, is given for as a 4.3 10 to the 5 TeV for the generic case and 89 TeV for the next flavor violation case, in the case of a strong coupled new physics, of course. And so what is more interesting is the top to bottom case where, for example, you assume a coupling that is a weak coupling, and so you scale for 0.03, for example. And that's something that, for example, in the next minimum flavor violation scenario is getting us closer to LHC rich, even if it's still a little bit high. So to conclude, this is the usual conclusion. I always end up saying that the analysis displays rather good overall consistency. There's still the issue of the DUB inclusive that it still looks like the outlier. I showed also the new physics contribution that are still allowed the current precision of the fit, and then the scale analysis that shows once again that the indirect searches that we do with flavor are not only complementary, but of course to direct searches, but they can be more informative in depending on the scenario we're looking at. And of course, I talked only about bottom quarks, down type quark, but there's still an eye to be kept on the up quark sector. Thank you very much.
Thanks a lot, Marcella. I see already a few people who want to have some questions. So I think the first was Sheldon Stone.
Hi, a very nice talk, Marcella. On slide 12, in the standard model fit, I thought you had a value for ASL of 0.32 plus or minus 0.03%.
Oh, sorry, the table here.
Yeah.
Yes.
Well, that's strange because the standard model prediction is a few 10 to the minus 5, and you have a few 10 to the minus 3.
This is this is the experimental measurements that we have.
No, the measurement is
input.
Your measurement is minus 2.1 plus or minus 1.7. Your fit has minus 0.32 plus or minus 0.03, which is like a 10 sigma effect, and it's I think it's 10 to the minus 4 for ASLD is the prediction.
Yes.
So you're showing non-standard model physics here if we were to believe this.
I can check. I might have done this one late at night.
No, but it's true. It's true. I just looked it up. The standard model prediction is a few 10 to the minus 4.
Ah, okay. So I'm not sure what's your question.
My question is, why doesn't this look like non-standard model physics in ASLD? If that's what you predict, which is what means that you're getting out of all the data, and the prediction is 10 times smaller.
I'm not sure I'm getting your point. I'm sorry.
Sure.
Sorry, somebody is trying to talk. Yes. No, okay. I mean, I'm not a super expert on semi-leptonic asymmetries, but this. So, if you're saying that the prediction is in line with what you're seeing, then I'm not sure I see the point. In
the prediction is a factor. The standard model prediction is a factor of 10 smaller than your prediction from your overall fit, which would indicate.
Okay, but if it's within the error, it means simply that.
No, it's not within the error.
Okay, I'll check that then. Okay, now I understood. Took me a while. Okay.
You're 10 sigma above.
Yeah. Okay, I'll check that. I might have done a miscalculation of the error.
Excuse me, but isn't this number multiplied by 10 to the 3? So in fact, the number is 10 to the minus 4. It's 3.2 10 to the minus 4.
That explains it. Thank you.
Oh, okay.
Oh, I see. Yes.
Yeah. It's 10 to the minus to the 3.
That would definitely explain it.
Okay. Sorry.
Okay, I think we have time for one last question. I see there was already Doris Kim who wanted to ask something.
Yeah. Can you go to page number 19? Hello.
Yes, I'm in my view. I'm on page 19.
Oh, okay. Then you have to go three more pages. Yeah, there. Here you are showing the plot of psi, S, and gamma. I heard that all three experiments updated their numbers during July. So I was wondering which version of numbers you are using.
So this I did this Sunday. So it should be the latest one for all the three of them.
Because I see.
I wouldn't put my hand on the fire because I really like it's complicated to disentangle some of the numbers. But what I did, don't use this one. This is really just me to help me visualize and help me make the average and then compare with some other average. Then I decided that I mean the LAC group is working on averaging that, so that they will at some point they will be talking seriously about this. As we are only using phi s. Even with a PDG inflation, I still get this. So there's no difference. But clearly there is an issue. Yeah, I think I'm not sure about LACB because LACB published an update on recently, and I'm not sure if I'm using this one. So I haven't checked, but I can easily check. And
yeah. I sent you an email. I think Atlas updated their number a couple of days ago.
Yeah, so Atlas, of course, because I'm also in Atlas, but I didn't do that with any Atlas information. I just used public numbers just to be sure.
Oh, I see.
So I know that Atlas updated. So because I knew the updates, I updated the numbers. They are not public, so there's no conflict of interest. But I have to admit I'm not sure 100% sure that I'm using the latest from LACB because what I want to use here is the KK only.
Oh, I see.
I don't want to use the pi as well because in principle there's different theoretical uncertainty that comes in.
Okay.
And also what we plan to do is to do to add a theoretical uncertainty once we have an estimate for this to the phi s measurement.
Okay, thank you. Thank you very much.
Thanks.
Okay, thanks a lot for the discussion. I think now it's time for the coffee break. I would propose to resume at 5:05, since we are a few minutes late. Okay, so see you later.
Bye.
Okay, welcome back. I think we can start this sub-session, which is mostly dedicated to Lepton flavor violation and Lepton universality, Lepton flavor universality. So the first talk is by Stefan Weber on the Lepton flavor violation at LHCb. So please, Stefan.
Yes. Hello. Let me share my slides. I think you can see them now.
Yes.
And hear me well, I hope. Okay, thank you. Yeah, thank you. So welcome to my talk. I will talk about Lepton flavor violations, and I will do this on behalf of the LHCb collaboration. In my talk, I will first give a brief motivation, and then I will basically present 3 searches for Lepton flavor violation. This is B2K mu electron, then B0 and B0S to tau mu, and finally B2K mu tau. So recently there were some tensions with the standard model discovered, for example, by the LHCb collaboration, and this especially within B to SLL transitions. So examples are the ratios of branching ratios, which suggests that we see Lepton flavor universality violations. And then we also have angular distributions of these decays. And in general, one can say that extensions of the standard model, which are able to explain these effects, they quite naturally should lead to sizable Lepton flavor violation contributions also. And examples for these models involve leptoquarks or heavy gauge bosons and many others. And on the other hand, in the standard model, these Lepton flavor violation processes are very much suppressed. So on the order of 10 to the minus 54. And this means this is unobservable within the foreseeable future. This means an observation of Lepton flavor violation would be a clear sign of beyond standard model physics. So that's why we are looking for them, and let me present some selected LHCb results. The first one is the decay B plus to K plus, and then muon and an electron. There are various models make predictions for this, and they range between several orders of magnitude, and this can go up to 10 to the minus 8. The best experimental limits so far come from the Babar experiment, and there one can distinguish between 2 chart configurations, and the limits are on the order of 10 to the minus 8. In our LHCb analysis, we have been using run 1 data. These are 3 inverse femtobarn at 7 and 8 TeV. The basic strategy is to trigger first on a high momentum, high PT muon. Then as the next step, require 3 charged tracks, which form a common secondary vertex, which is incompatible with any primary vertex of the event, and which are identified as a kaon, muon, and an electron using our PID detectors that we have. To calculate the branching ratio, we don't usually do this in absolute terms directly, but we normalize this to well-known decay channels. And in this case, this is the decay B plus to K plus and a J psi, with which then decays further to a dimuon pair. And as a control channel, we also use the dielectron pair. So in the analysis, we have to reconstruct an electron. This is a bit complicated because this can radiate Bremsstrahlung. But within our calorimeters, we are also able to recover partially the energy loss from Bremsstrahlung. This does not work perfectly, but with this, so we lose a little bit of resolution, but we can partially resolve this. And within the analysis, then different fit functions can be used for the different cases of whether we have photons of Bremsstrahlung recovered or not. In the analysis, the main background consists of partially reconstructed B decays. So you can have this case where you have a double semi-leptonic decay, which can produce this pair of leptons. And for this, one can impose mass constraints on combinations of the decay products. Also, it's possible to have a germanium decay with one of the leptons misidentified as a kaon, and this can be cured with mass vetoes. Then in the analysis, we also employ 2 boosted decision trees against combinatorial and partially reconstructed background. Yeah, these 2 invariant mass distributions here then show that we do not observe any signal in the region where we look for it, and that's why we can give upper limits for this decay, and we arrive to a value of 7 times 10 to the minus 9 for the K plus mu minus E plus charge combination, and 6.4 times 10 to the minus 9 for the K plus mu plus E minus. And both of these are the world's best limits so far. Next decay which I want to present is the B0 or B0 sub S to tau muon pair. There the model expectations go up to the order of 10 to the minus 5. The best experimental limit on the B0 decay comes from the Baba experiment. It's 2.2 times 10 to the minus 5, while for the B0 sub S, there is no experimental limit so far. The analysis strategy is a bit different. Again, we use 3 femtobarns from run 1. Again, we trigger on a high PT muon, but in this case, we have to reconstruct the tau from its decay products. For this, we use the 3 pion neutrino decay of the tauan. And then again, we normalize to a well-known normalization channel, which has a similar topology as our signal decay. We can reconstruct the tau momentum with a 2-fold ambiguity from the known flight direction, and under the assumption that we have tau mass and that we have massless neutrinos. And one can also use the fact that the tau decays mainly via the A1 and rho resonances, and this helps also to reduce the background from other particles. We can also use same sign tau mu pairs as a model for the combinatorial background, which is then used for the training of the BDTs. An important background are also partially reconstructed BDKs. This can be distinguished from the signal with help of decay time, isolation variables, and can be suppressed with mass vetoes. Here I illustrate that the B0 and B0S, the peaks overlap, and that's why we perform our search for the hypothesis that we have the one or the other. The search is performed in bins of a final BDT. Here, for illustration, I show the bin with the highest signal probability. Again, we don't see a signal. That's why we can give confidence limits. So for the B0 sub S, we have 3.5 times 10 to the minus 5 at 90%. And for the B0, 1.2 times 10 to the minus 5, which is the world's best limit. And the other one is the first limit so far. Then the final decay, which I want to demonstrate, is the B plus to K plus mu tau. Again, model expectations reach up to 10 to the minus 5. Best experimental limit, 2.8 times 10 to the minus 5. Here, the analysis strategy is a bit different. We use both run 1 and run 2 data. So this is 9 inverse femtobarns. And we actually consider B plus from the decay of the B star sub S2. This means we require a pair of a kaon and a muon from a secondary vertex plus an additional charged track. And then we can calculate the missing mass squared of this track. And we expect a peak at the tau mass for the signal. This is illustrated here. So for a signal, we expect a clear peak. Again, we use a normalization channel, which is B plus to J psi K plus. We can also extract the fraction of which of the B's come from this B star S2 decay and which are independent of this. And then we have several backgrounds which can be suppressed again with the help of boosted decision trees. And the remaining backgrounds, we expect a smooth distribution in this missing mass squared distribution. And also in this case, we don't observe any signal, and we can extract limits from this. And our limits are 3.9 times 10 to the minus 5, which is comparable to the world's best limit. In conclusion, we can say that an observation of lepton flavor violation would be an unambiguous sign of beyond standard model physics. So lowering the experimental limits is very crucial also to constrain phase space of theoretical models. And LHCb has a very rich search program for these lepton flavor violations, of which I presented you a few examples. And often we are able to produce the world's best upper limits, or we are close to. A little bit of outlook. So of course, in the future, we want to collect more data. This is about 23 inverse femto ones in run 3. We will use a purely software trigger in this run, which will help us to cope with the higher luminosities. And another aspect which I would like to mention is that we are also able to measure lepton flavor violations in baryons, which can give complementary information. So for example, we have different dynamics due to the half integer spin of the baryons. And these are abundantly produced. And as one example, the lambda B to lambda E mu decay is currently being analyzed by LHCb. So thank you for your attention.
Thanks a lot. So let's see if there are any comments or questions from the audience. I do not see any, but okay, I have one. I've seen that you have, among other things, you have presented the upper limits on the branching ratio of the B0 to mu tau and the B plus to K mu tau. But I was wondering regarding the, let's say, theoretical interpretation, which one would be more sensitive between the two, for instance, on leptoquark or new particle, or if, I mean, there are different models which are, let's say, shared, like there is one model in particular for which the B0 mu tau is more sensitive rather than B plus. If you could comment a bit on this.
No, I'm not really an expert on the models, and I think they give vastly different limits depending on the flavor of your models. But I think one thing one can say that really for this decay involving a muon and electron, we go very deep. We go in the order of 10 to the minus 9. While model expectations, indeed, they reach up to 10 to the minus 8. So I think there we are indeed doing quite some restriction of the phase space of these models.
Okay, yes. Okay, no, my question was more about the mu tau, but in any case, it's clear that the search is a very nice and interesting I mean, all the ones that you have presented. Okay, so if there are no more comments or questions on these, thanks again, Stefan. And we move on to Olsir, who will present a review of the lepton flavor violation at LHC.
Okay, can you hear me?
Yes.
Okay, very good. So let me share the screen. Oops. Okay, so can you see it?
Yes.
Okay, very good. Okay, thanks a lot. My name is Osir, and I'm very happy to tell you a bit today about flavor physics that can be done at high PT. And in particular, I'll continue the discussion on lepton flavor violation. And so I'll present these results from this recent publication of ours. And I'll start with a brief introduction, which is our motivation here. So basically, when you do flavor physics, the ultimate question that we would like to answer is the flavor problem. And the flavor problem is basically the fact that in the standard model, we don't have flavor symmetry. That would be equivalent to the gauge symmetry, the gauge sector. So that flavor is pretty much unconstrained. And the consequence of that is, as you know, is that we have many parameters in flavor. So the fermions mass and mixing, which can be described by means of the Yukawa interactions. But then we have to extract this information from data. And this is a problem not only because flavor becomes then highly non-minimal, but most importantly by the fact that when you look at these values for the fermion masses or the mixing parameters, we see clear patterns that suggest something beyond the standard model. So, so our goal then is to look for any signals of this beyond standard model flavor dynamics by using low energy observables. And the key observables are the ones where flavor is violated. And lepton flavor violation, as we just heard, are particularly interesting. They are interesting because they're forbidden in the standard model by accidental symmetry. We know that the symmetry should be broken because neutrinos are massive and oscillate. But even if you plug in the neutrino masses, assuming that there is no other dynamics, we see that all these processes are completely unobservable. So that's why we say that they are very clean, and that's why it's important to look for them experimentally. And from the experimental prospects, we also have a very promising scenario for the coming years as well. So this is the case, they can be in purely leptonic observables, such as the tau and muon decays, and here that there are many experiments that are pushing in this direction. And we also have the hadronic probes with the case of kaons, D and B mesons, which are quite interesting. And these are the ones I'll be talking about today. So the goal of my talk is to tell you what can we learn by using proton collisions. How can we get some indirect information on these decay modes? And a further motivation for that, that I'll mention very briefly, are of course these B physics anomalies, because here it suggests that there is new physics around the corner with lepton flavor dependent couplings. And nowadays we know that the only particles that can actually explain these discrepancies are the so-called leptoquarks, and they must couple to muons and taus. So here, if you just swap the flavor in one of these legs, you see that's almost unavoidable to have lepton flavor violation to some extent. So there's a common prediction of these viable models, and that's why it's so important to push in this direction, like we're doing now with LHCb and BEL2. Okay, but today I'll be talking about LHC. And the main idea behind this talk is the following. When you collide protons, that's also a flavor physics process. So actually, the cross-section for proton-proton into dileptons that can be factorized into a partonic cross-section where you can have 5 different quark flavors. And then we have these luminosity functions, which depend on the quark PDFs and that weight the different contributions to the total cross-section. And as you see here in these plots, these luminosity functions are bigger for the first and second and third generation, first and second generation, and then they are smaller for the big quark, for example. And the approach we use is effective field theories because this is the most economical one that we can have. And the only assumption is that new physics is sufficiently heavy. And then this effective operator here with 2 quarks and 2 leptons can be constrained either by flavor, by some specific meson decays, or by looking at proton-proton collision by this partonic interaction here. And then in the following, I'll show how these 2 results can be very much complementary to each other. So this kind of analysis at high PT is possible because of a very simple argument, which is that when you have a dimension 6 operator, like the ones I mentioned before, if you compute this cross-section, assuming that the EFT is valid, you get something that grows with the square of the energy. Okay, so, and that's of course different from all the standard model backgrounds, since the standard model is normalizable. So what we do is to take data from proton-proton going to the different lepton combinations, and then look really at the high energy beams, because here we know that signal over background will be the largest possible. And when you look into this, there are many operators that can contribute to these partonic processes. They're listed here in this table. So within the standard model of EFT and also the broken phase. And basically you have vector operators, scalar operators, and tensor operators with the different chiralities. So you can try to compute this partonic cross-section, and then you get this formula here. So we have this energy enhancement that I mentioned before for all these operators. And the funny thing is that they do not interfere with each other at high energy. And that's a useful input that I'll use in the following. So the only thing we're left are these multiplicative factors here that tell you how the limits on each of these operators is scale when you compare them. So just a proportional factor. This was for total cross-section, but then we have, of course, checked that when you impose the selection cuts from this experimental analysis, the total cross-section changes, but this proportion between the different contributions remain more or less the same. Okay, so now let me show you some results. So I'll consider the tau to mu Lepton Flavour violation, and I'll pick one example of operator, which is this V minus A, V minus A one. So vector with left-handed fermions. And here I have a Wilson coefficient with 2 quark indices and 2 lepton indices, which are mu tau. And then here you see the LHC limits that we get with current in blue and red future data for each quark transition. And the colored bands here are the limits that we get from flavor physics observables. So what are these limits from flavor? So here, for the light quarks, they come from tau decays, tau to mu, and some meson. So in the case of the B2S and B2D transition, these are the decays we just heard about in the previous talk. So leptonic and semi-leptonic B decays. And there is also the quark flavor conserving transition. And here we have to use quarkonian decay, so J psi and upsilon. And finally, there is the CU coupling. And here, actually, there's no meson decay just because it's not kinematically allowed. So the D and tau mass are too close to allow you to have a decay. And what is interesting is that the limits are very complementary. So in many cases, like down here and up here, flavor does much better than LHC. But there are situations where LHC limits can be much more constraining than flavor. So these blue bands here, actually, they extend beyond the picture, so you don't see them. So they're very complementary. And this remains true when you look at all the lepton transitions, E mu, E tau, and mu tau, as you see here in this plot. So the ones where LHC can give you some useful information are the flavor conserving transitions, and also the charm quarks sometimes, because we don't have a meson decay. Okay. So now, just to give you a feeling of these results, let me make a small exercise here. So again, let's assume this operator, and then let's take the limit that we get from high energies with proton-proton collision, and let's just take this coefficient and compute a branching factor that you can try to measure experimentally. So for each of these decays here, we took the LHC limit and we saw what is the sensitivity that we're getting with the LHC, assuming keeping this assumption. And these are the results that we compare here with the experimental limits today and the future prospects that we were able to find. And the way to read this is, for example, if Bell2 wants to improve the flavor violation tests in upsilon decays, so they have to push these limits 4 to 10 to minus 6 to be 10 to minus 7 to be competitive with what we have now, and then 10 to minus 8 in the future. And the colored are actually the limits that are the most constraining ones. So you see, things are very complementary, and it's very important to have both pieces of information when you want to constrain new physics. And of course, here there is an assumption, which is that I only have this operator which is left-handed. Then you might ask what happens if the other operators are present, such as the scalar and tensor ones. From the point of view of LHC, it doesn't change much because, as I said, I mean, the cross-section changes by a factor of 1 to 3/4 or 4. So there is a small numerical factors that can be taken into account, and we give a full prescription in our paper. But for flavor, things change a lot. So the choice of vector operators here was intentional because here the comparison was easier. And we knew that in this case, LHCb had a better chance to give meaningful results. But for the scalar operators, the situation is a bit different. First, because when you run these operators from the TV scale down to the field GV, where you try to measure these decays, you see that for the scalar operators, we have an enhancement. And also scalar and tensor operators can mix via electroweak running. Okay, so that's one factor. And the second one is chiral enhancement, because when you look at pseudoscalar meson decays, with a vector operator, they're going to be suppressed by the lepton mass. But as soon as you turn on the scalar operators, there is a chiral enhancement of order md over mu, which is huge, and that can improve the signal. So just to give an example, if you look again this D0 to mu decay for the vector operator, we found that high PT was a bit more constraining than flavor, but for the scalar one, flavor is much better. So factor of 10 more. So this tells that flavor and LHC are complementary, not only about the transitions that you can probe, but also the chiral structure of these operators. And that's all I wanted to say. And so the brief summary is that there is a lot of possibilities to do flavor physics at the high PT. So today I spoke about this PP to leptons with different flavors, but there are other publications that studied dileptons with same flavor or the monolepton signatures, and they were motivated by other problems such as the B anomalies or charm physics. And so these are all meaningful constraints that should be combined together and also combined with what we have for flavor when we try to look for the physics in order to be the most sensitive to it. Thank you very much.
Thank you. So any comments or questions from the audience? I do not see any. Okay, so maybe I can ask you something. So I think, okay, everybody, given the B anomalies, let's say, is focusing mostly on the mu tau, because of course it should, if there is any leptoquark or similar, it should couple, let's say, more likely with heavier leptons. But I was wondering how suppressed it would be if you said it would couple with, for instance, I mean, looking at the same particle with the muon electrons instead of muon tau. Is it that strongly suppressed? How much?
So yes, the point here is that to explain the B anomalies, you need a large coupling to the tau and a slightly smaller coupling to the muons. So when you compute these rates, you get not only an upper limit on this P to S mu tau, but also a lower limit. Now, when you think about the electron and muon transition, there we have also an upper limit that you can compute if you assume that you have a coupling to the electrons, but there is no lower limit because the couplings to electrons could be super suppressed because we have no hint of new physics there. So that's, I think it's important, of course, to push these limits because they're always useful to have a feeling of if the anomalies are confirmed, what is the pattern of flavor that we should have in these leptoquark couplings. But it could be that super suppressed that we never observed.
Okay, but let's say it would be a kind of a fine tuning, I guess. In any case,
yeah.
Okay.
Well, not a fine tuning because I mean, so look, the Yukawas in the standard model, they're very hierarchical and they're bigger to the third, second, and first generation. So you could have something similar here.
Okay. Thanks a lot. Okay, so I would propose to move on, and now there is Beatriz Garcia Plana with the universality test with the semi-leptonic B decays at LHCb.
Yes, hi.
Hello.
No me deja compartir. Do you see the screen?
Yes.
Okay.
Okay, you can start.
So good afternoon to everyone. Today I will talk about lepton universality test using semi-leptonic B-hadron decays. This is the outline of my talk. First, I will make a small introduction about the concept of Lepton Flavour universality and how we can test it in semi-leptonic decays. Then we will move on to LHCb results. In particular, we will see the muonic RD star, the hadronic RD star, and the ICHEP psi. Then we will see some future analysis and future strategies, and we will end up with the global pictures and some conclusions. So within the standard model, the electroweak coupling between the gauge bosons and the leptons are independent of the lepton family, and this is called Lepton Flavour universality. LFU is one of the main ingredients of the standard model, and therefore any sign of violation would be a sign of new physics. Actually, it exists many models beyond the standard model that contain new interactions that involve the third generation of quarks and leptons, such as charged hits, leptoquarks, Z prime, or W prime. There have been done many searches of this violation, and in particular, we studied two different kinds of transitions. Within charged currents, so V2C lepton neutrino, and in neutral currents, we study the V2S LL transition. In this talk, I will just cover the charged currents one, but if you want to learn more about neutral current, don't miss the talk of Carla on the 31st of July. So why semileptonic decays? Semileptonic decays offer us a good scenario to test Lepton Flavour universality, and this is done by means of the coefficients RHC, which is defined as the branching fraction of a B hadron going to a C hadron tau nu with respect to the branching fraction of the same B hadron going to the C hadron mu nu, where a C hadron could be D or D star, D0, D plus, DS, lambda C, j psi, and a B hadron could be a B0, B plus, lambda B, etc. This is a three-level decay mediated by a W boson, and therefore, if new physics coupled just to the third generation, this kind of transition are sensitive to new physics component at the tree level. There are many advantages from the standard model. First, it's partial cancellation of hadronic form factors in the ratio. Then the high rate of charged current decays. For instance, the branching fraction of V going to the star tau nu is about 1.2% in the standard model. Then another aspect that I want to comment about these coefficients is the deviation from unity due to the different lepton masses between the tau and the mu. What happens at LHCb is that these kind of measurements are very challenging because we are dealing here with neutrinos and therefore with missing kinematic constraints. So in order to obtain our B momentum, we need to make some approximations, and we will see in the next slides how do we do it. So basically, we have two decay channels for the tau, the muonic mode in which the tau decays in a muon and two neutrinos, and the hadronic mode in which the tau decays in 3 pions, a pi 0 and a neutrino. The first measurements of RD star in a hadron collider was done using the muonic decay of the tau, so the tau going to mu and two neutrinos. And here the coefficient RD star is defined as the branching fraction of V0 going to D star plus tau nu with respect to the same decay but with a muon. Some features about this analysis is that since we have missing kinematic constraints, we have to make what is called the rest frame approximation. So here, the momentum of the final visible state, so the D star and the muon, is scaled by the mass of the B with respect to the mass of the final visible state. With this approximation, we obtain a resolution of 80% on the momentum of the B, which is good enough to preserve signal and normalization discrimination. We can see this on the right. So in green, we have the projections of the variables of the missing mass, the energy of the muon and Q square, which are the one with most discriminating power. So in green, we have the Monte Carlo truth, and in pink, we have the Monte Carlo reconstructed. So it means after we include the detector effects. So here we can see that we can differentiate between the signal component and the normalization one. For instance, for the missing mass, in the case of the normalization, its spectrum, it's peaking in 0. The spectrum of the energy of the muon is harder, and it ranges from 0 in the Q square variable. In order to obtain our coefficients RD star, we perform a three-dimensional fit to the variables that I just present, so the energy of the muon, the missing mass, and Q square. And here we have the projection of the three-dimensional fit. In red, we see the signal component, and in dark purple, we see the normalization one. So this was the result that was obtained for the R11, with its intention with the standard model prediction at the level of 2.1 sigma. Let's move on now to the RD star hadronic. Here, the tau decays in 3 pions, a pi 0 and a neutrino, and therefore we have overlapping signal decay mode. Actually, what is measured here is the coefficient that I call kappa, and in order to obtain it, we need to measure the signal yield, the normalization one, and correct them by the ratio of efficiencies. Again, we need to make some approximations in order to reconstruct the V and the tau momentum. An important feature about this analysis is that the signal and normalization channel share the same visible state, so D star and 3 pions. And therefore, most of the theoretical and experimental uncertainties are cancelled out in the ratio. Once we have the kappa coefficient, RD star is obtained by multiplying it by the external inputs, which are well known with a 4 and 2.2 precision. So in order to obtain RD star, we perform a three-dimensional fit. We have here the projection of the tau decay time, Q square, and BDT. In red, we have the signal component, and in orange, the main background. So this is the result that was obtained, which is in tension with the standard model prediction at the level of 1 sigma. Then we can generalize the analysis that we have done for RD star in the VC sector, and we obtain the ICHEP psi coefficient. The measurement that was done using the tau decaying in a muon and 2 neutrinos. And in order to obtain our coefficient ICHEP psi, we perform a three-dimensional fit in the missing mass, the decay time, and Z, which is a variable that depends on the energy of the muon and Q square. And the result that was obtained is in tension with the standard model at the level of 2 sigmas, depending on which theory you are taking. So we may wonder now, which is the global picture. In the case of RD star, we have in the lab the different experimental measurements. So the one corresponding to Babar, 3 from Bell, and 2 from ICHEP, which is the green bar. And then we have the standard model prediction, which is the red one. So the RD star wall average is in tension with the standard model prediction at the level of 2.5 sigma. If now we take into account all the RD and RD star measurements, we have the average in the red ellipse. And if we compare it with the standard model prediction, we see that overall it's in tension at the level of 3.08 sigma level. Some words about the future. Here we have the projected uncertainty for Bell and ICHEP for all our RHC coefficient. For instance, we can compare the 2 orange curves, which correspond to the Bell RD and RD star prediction, and we can compare it with the one from ICHEP that are the 2 green. So it's expected that both experiments will be comparable in the future. Then we are expecting new results coming from updates or using the run 2 of all the analysis that I just presented. And there are many analyses ongoing, so RD0, RD+, RDS, etc. And also combined measurements of RD and RD star for both the hadronic and the muonic mode. Then it's planned to perform some form factor measurements, and in particular, the VS going to DS star, it's already done. Then some angular analysis. And in the future, after the upgrade 1, it's planned that ICHEP will collect 50 inverse femtoarm. And we see here the projection of the integrated luminosity. So it means that we will have a 5 times more luminosity than what we have at the end of the run 2. Conclusions, we have seen that Lepton free universality violation, it's a clean road to new physics. There are intriguing tensions with the standard model in the ratio of branching fractions in B2C lepton neutrino decays. All the results that I present here were done using the run 1 data. And we have 9 femtovars embed at the inverse at the end of run 2. So there is an exciting program ahead. About the systematic uncertainties, many are assumed to scale with the accumulated statistics, and others will be improved with external measurements as the one coming from Bell 2 or Best 3. So stay tuned, and thank you very much for your attention.
Okay, thanks a lot. So any comments or questions from the audience?
Hello, hi.
Yes, please.
So I want to know, are there any updates on the experimental side in the measurements of this BS2 DS star LNU means Lepton Flavour universality test in those decays?
I don't hear you well, but I think that you were asking for this coefficient, the RDS, yes. Right? Okay, so it's ongoing already. So I don't know exactly when it will be finished, but next year probably.
Oh, thank you.
Okay, thanks a lot. If there are no other comments or questions, I would move on. I don't see any other. So thanks again.
Thank you very much.
And now we go to Joel Swallow, who will present Lepton Flavour Lepton Flavour and number violation at the NA62 experiment.
Hi, do you hear me and see the slides?
Yes.
Okay, great. Let me know if there's a problem. Okay, so as Karim said, I'm going to be talking to you about NA62 searches for these lepton number and Flavour violating decays. This is the quick overview of the talk. So I'll tell you something about the NA62 experiment and particularly the new result on the search for K goes to PAM UE decays, and then some context related to the other searches that we're doing. So the NA62 experiment is based at the CERN North area. We're at the end of an extraction line from the CERN SPS, and you can see on the left that we sit roughly at the center of the LHC ring. The primary goal of the experiment is the measurement of the ultra-rare K goes to pi nu bar decay, but I won't go into any detail there because there's a very recent paper on the archive from the 2017 data analysis, and there was a nice talk yesterday on our brand new result. Instead, I'm focusing on the broader physics program at NA62. So this was also covered nicely in the last couple of days with the rare K decay, K goes to pi mu mu, covered yesterday, and also exotic searches, in particular for heavy neutral leptons, also the subject of a recent paper and a talk. The Run 1 dataset was taken from 2016 to 2018, and in this talk I'm focusing on the data from 2017 and 18. Okay, as has already been covered quite well so far, and I won't labor the point, in the standard model, we have this conservation of lepton number and lepton flavor numbers, which is somehow an emergent property, but we've seen with the neutrino oscillations that these individual flavor numbers can be violated. So it's worth checking to see if we can also violate them with the charged leptons as well. So in particular, you could have scenarios with in K decays where you have mediation via Majorana neutrinos, as you see on the left-hand side, or mediated by leptoquarks, as shown on the right. In any case, the experimental signature here that we would look for is a pion and 2 leptons with the decay consistent with closed kinematics. If we then go to the next slide, you see just a picture on the left and the schematic on the right of the NA62 experiment. So we're using an unseparated secondary hadron beam that's produced when protons from the SPS hit a beryllium target. The experiment is very long, as you can get an idea of on the picture and in the schematic of the detector, and this is governed by the momentum of the kaon, which is 75 GeV, and the Lorentz boost in the lab frame. I won't go into too much detail on the whole detector, but just to comment on how it's used in this analysis in particular, I told you that only 6% of the secondary beam is kaons, so we tag these with the Cherenkov detector, the K-tag, with a very good time resolution. Downstream, we're looking for a 3-track event, and we reconstruct the tracks and measure their momentum with the straw spectrometer. And we can then reconstruct a vertex in the fiducial volume. So this is indicated, it's a long vacuum tank region in which we're reconstructing this. For particle identification, we're using this ratio of E divided by P, where E is the energy deposited in the liquid krypton calorimeter, and P is the track momentum. And then also we can use the muon Vito3 detector, which is at the very end of the experimental apparatus behind the calorimeter and an iron wall, which is sensitive to veto or identify muons. There is a hermetic veto system at NA62 with 12 large angle vetos surrounding the vacuum tank, small angle vetos, and the liquid krypton calorimeter. In this analysis, we're using the large angle vetos to reject stray photons. The tracks must be in time, and we're using charged hodoscopes to make these timing measurements. And in the end, we're building an invariant mass of the Pi-MeV candidate final state with the resolution of about 1.4 MeV. On slide 7, you see the search strategy. We're searching with 2017 and 2018 data using a blind analysis strategy. There was actually 2 independent analyses, and these were cross-checked for the final result. At NA62, we have a 2-level trigger system with hardware level 0 and software level 1. And these triggers that we're using for this analysis, as shown in the table, are run concurrently with the Pioneer bar trigger and downscaled by certain factors. The inefficiencies of these triggers importantly need to be accounted for in the analysis. We're using a minimum bias multi-track trigger to collect the normalization channel, which is the K goes to 3 pi decay, which is the most common 3-track kaon decay with a branching ratio of about 5.6%. We're then using all 3 of these triggers to collect the signal candidates, and the overall effective number of kaon decays in the fiducial volume that you can use then for this analysis is about 10 to the 12. There's quite a number of backgrounds that have to be considered in the analysis, and these enter by two ways, either by misidentification or decays in flight. Just to give a feeling for the misidentification, you see on the right the misidentification probability as a function of charge times momentum for the processes of pion looking like electron or positron, or vice versa. And this comes from using this E over P ratio that I was discussing before, where the electron is basically depositing all of its energy in the calorimeter. So you have an E over P ratio close to 1. There is also the decays in flight that must be considered. Importantly, the decays in flight of the charged pions, either to a mu neutrino or e neutrino, and the former is more important in general because its much higher branching ratio is there. There is also the pi0 Dalitz decay, which is a particular nuisance in one of the 2 channels I will talk about in a moment, and this means there's a dedicated cut used for this, to reject this. Here you see the invariant mass distributions on the left for the pi minus mu plus E plus channel, and on the right pi plus mu minus E plus. We have a blinded region, which was kept blind for the optimization of the analysis, which is centered on the kaon mass, and the central signal region that you can see indicated sits at the kaon mass. We then have these sideband control regions that are also indicated. Above this blinded region, you can see we expect a certain number of events as indicated, and the observations match quite well to these expectations. If we move forward now, we look at the sidebands. We can see again that the agreement between the expectation and the observation is good. The acceptance for the two channels are also indicated on the slides. So for the pi minus channel, it's about 5%, and it's about 6.2 for the mu minus channel. And the main difference here is this additional cut to reject the Dalitz decays, which I already mentioned. You can see also the single event sensitivity, which is calculated here at the level of about 10 to the minus 11, calculated using the equation at the bottom of the slide. Okay, so now we go ahead to the result. And as we saw, the expectation in both channels is about 1 event. And for the pi minus channel, we observe 0 events in the signal region. So we set an upper limit at less than 4.2 times 10 to the minus 11 and 90% confidence level. And similarly, in the mu minus channel, we actually see 2 events. And in the same way, we set an upper limit at less than 6.6 times 10 to the minus 11 at 90% confidence level. On the next slide, all I'm doing is summarizing the results. So we see the acceptance for the signal, the single event sensitivity, and the expected and observed number of events. Takeaway message here is to compare these new limits that we've placed with the old previous best limits, and we see we've improved by roughly a factor of 10. This goes into the context also of the recent studies that we've published last year on the pi minus and 2 same sign, same flavor leptons. So pi EE or pi mu mu. And again, using quite a similar analysis strategy, we observe these upper limits on the branching ratios of these processes. This brings me to the conclusions slide. So alongside these nice headline pi nu bar studies at NA62, we have this broad physics program with the world leading sensitivities to these rare and forbidden kaon decays. I invite you to see the other nice talks at this conference. In the table, I summarize the picture for the lepton number and flavor violating searches at NA62. So I've just shown you the top 2 where we've improved the previous limits using just 2017 data, and this was published last year. And now in this talk, we're showing the improvement in the pi mu E searches, which improved by a factor of 12 and 8 for the 2 channels using both 17 and 18 data. We're going to resume data taking in 2021, and already we have our eye on some other channels, as you can see in the table. So stay tuned for future updates on this. Thank you.
Thanks a lot, Joel. So any comments or questions from the audience? I don't see any. Okay, so maybe you can just tell us more or less, do you have an idea on how big could be the improvement on these limits, adding, let's say, the next data taking data?
Okay, so when we resume data taking, the intensity will be a little higher, and so there's definitely potential to improve in terms of taking data, and we're not background limited in these analyses. So this is the good news. One thing that we have to be wary of is that because we're going to this higher intensity, the trigger strategy might have to change a little bit. So this might mean that relatively we're taking less data for these kind of analyses in the future. But overall, it could be possible to improve by a factor of order 5 potentially with the next data set.
Okay, that would be very good. Yes. Okay. Okay, thanks a lot, Joel. I don't see any other comments or questions, so I would propose to move on. And of course, if anybody, I remind anybody that there is a Mattermost channel, so if you want to have more discussion about some particular topic, please feel free to have a discussion there. So now we go on with the next talk, which is by Amarizzoni on the Lepton Flavour universality violation and their repercussion. Hello?
Yeah, so just give me a second. I guess I'm going, oh yes, so this is the video. Okay, very good. How can I get the full screen here? All right, so can you hear me?
Yes, you can start.
All right. So I'm not sure why I cannot use the full screen, but I think I'll go ahead with this. So yeah, I will be talking about the flavor anomalies, and in particular, because of the shortage of time, in the context of R parity violation, SUSY, and the 3D I'll explain in a minute. So anyway, this is papers with Wolfgang Altman, Hoffer, and Dave for the last 3-4 years. Second in a sequel, this took place a couple of years to get all the pieces together. All right. Okay, so I'm sorry, I don't know why the next. Okay, so here's the outline, and I'm going to remind you the anomalies, and then the point is this RPV SUSY has lots of reasons for going after that, and we are putting the 3 there for because of starting from about 2017, we have made the for good reasons that the 3rd generation super partners are the lightest, and then I'll explain some 3 special cases for which we study this scenario. So of course you all know about the anomalies, the charge current anomaly and the neutral current anomaly, and there are all 3 experiments showing deviations in the simplest 3-level charge current case on the left, and amounting to at the moment about 3 sigma, and on the right is the LACB RK star. This is about 3.5 sigma. And the fact, of course, we always need to worry, there are so many experiments from the charge current case. There are altogether 11 of them, and all 11 central values are higher than theory. And again, I don't have time to spell it all, and this needs to be kept in mind. So it seems as if there is no way out, and we have seen the breakdown of the standard model. But this is, in my opinion, we cannot assume that easily, because so this is category of the experiment. 3 different major B experiments are involved: 3 with B to D, 7 with B to D star, 1 with BC to psi, 9 with tau going to leptonically, and 2 with tau going hadronically. Each and every 11 of them show central value higher than standard model. So it seems as if the universality is breaking down. But I think there are cautionary things that we have seen in the past in our history. And this is a 10, 12 years history, and long ago in the Michel parameter, which is standard model V minus A, predicts 0.75. The experiments for 10, 12 years kept on seeing it below. And then somehow magically it starts to come in agreement. So things like this can happen. There are sometimes the systematics are there. And I'll elaborate later on more. And so anyway, then I also bring in here G-2, and G-2 Buchanan experiment is deviating from theory by 3.5 sigma. On this slide, only the phenomenology theory dispersion relation is shown. The lattice has made a lot of progress, and it's about a factor of 2 larger errors at this point, and then the dispersion theory, but it will catch up pretty soon in next year or 2. And I'm also showing here, not showing here at the moment, the next slide for the balloon experiment called Anita, because the systematic errors are not under control. I don't like to show that. So in the bottom are the pool for all of the 3 experiments that I talked about: RD star, RK star, G-2 mu, and whether there's some issues in our mind is that theoreticians, we take the liberty, poetic license of leaving out Baba, because Baba has a lot of deviation there, and if you leave out those, and you can see that when you take all of these 3 different types of experiments, the pool reduces to 4.6 sigma, but otherwise it's over 5 sigma. So it would appear as if this is compelling, but as I said, in each case, there are worrisome features. But in any case, And this is a Anita balloon experiment, 2 gigantic energy 10 to the 9 electron volt neutrinos, and both of these events people have argued cannot be understood from the standard model. So I don't have the time to explain all this. But systematic errors are worrisome. So we take Anita along with the others that I mentioned, and we are looking for a SUSY solution, in particular RPV. The reason for that is the following. So starting in the 2017 paper, what we said was the reaction B to D star tau or leptonic decays is the B going to tau. This is the 3rd generation, and and perhaps it is all related to the problem that we have Higgs naturalness, Higgs stability under radiative corrections, which is shown in the picture below. And so we want to, we just proposed that let's consider the 3rd family of super partners to be the lightest. If that happens, the proton decays, it becomes irrelevant and largely irrelevant. And so you go from the minimal MSSM to, you can go to R-pair evaluation. R-pair evaluation becomes you know, a very good candidate. In fact, remember that R-pair conservation is just put in by hand because you want to protect the proton. But in this case, when those super partners, 1st and 2nd generation, are super heavy, only the 3rd generation is lightest, that proton decays are not really relevant. So we go, RPV is very natural. And in RPV, then lepton universality evaluation becomes natural, and lepton quarks become natural, and G-2 and epsilon prime, things like this, you can accommodate. And at the LHC, looking for signatures for our evaluating theory is harder. So all of those reasons may make us wonder if this is the way things are going. So anyway, so this is again saying that the 3rd generation is taken to be the lightest, super partners are taken to be the lightest. And a key point here is that one of the best interesting things about SUSY is that it gives you gauge coupling unification. And you can see here, we show that explicitly, whether you are 1 generation or 3 generation, the gauge coupling unification stays. It's just that the scale stays, it's just that coupling shifts a little bit. All right, so it has that nice feature too. So more on that, why it is, so there are these effective Lagrangians that come in for quark lepton interaction and lepton-lepton interaction and all that. And we use those, and there are a bunch of diagrams of this charge current, and this is the neutral current. For the neutral case, both tree level and loop level have to be kept because you want to get the sign correct for RK and RK star. The signs are correlated, and having both tree and boxes are important. So then this is for muon and also for G minus. Anita, I show you all the pictures, and a lot of the calculations are available in literature. We had to put them all together in the context of scenarios that we are studying. So then to simplify things, we take 3 specific scenarios, benchmarks. One is very CKM-like. In CKM, you know that when you go from 1st generation to 2nd, you have to pay a price. And when you go from 1st to 3rd, you have to pay an even higher price. So we went through that, and in so far as the 3rd generation super partners being lightest, there was a very nice paper, I'll give the reference later, which formally put this in the context of a U2 cross U2 flavor symmetry. And this also has, in each of these 2 cases, there are 3 independent couplings, and the 3rd benchmark scenario, no such symmetry is imposed. And again, there in each of these 3 cases, there are 6 free parameters and 3 independent couplings are being used. So this is the case 1 that I mentioned, and you look for a common solution to all the anomalies, and a common solution cannot be found. In particular, G-2 cannot be accommodated, and the others perhaps could be. And then we look for case 2. This is the reference for the very nice idea of making a 3rd generation super partner lighter, where the others are very heavy. And in this case, you do find a solution in green there which overlaps. And there are some issues with perturbability in the horizontal scale up there, but you don't need to go there. It's just an indication. All right, then the 3rd one is when there is no symmetry. Again, you are able to accommodate all of them, and there is an overlap. And this is pretty interesting that that you are able to accommodate the things if the anomalies stay with you. Of course, if you also have the capacity of taking whichever one does not stand for the scrutiny, taking it out and seeing what happens. So it gives us a parameter space. The key point here is that the bottom mass has to be around 2 TeV or heavier, and then you have to look at our papers for other masses and so forth. I don't have the time to do that. So very interesting things happen in this kind of scenario for tau flavor violation decays. In particular, tau to mu gamma is quite enhanced. And B decays, the most interesting B decay is tau. And it has a rather large spread ratio, whether you go inclusive or exclusive, that's pointed out. And experimentalists ought to go after them. This would be a very important key. So what we are trying to do here is ask for repercussions of under this theory of the anomalies, and that's what we are doing. And that's the first table. And the bottom below shows what you do, what happens. You're making no theoretical assumption. This is crossing symmetry. You see RK star, which means B quark goes to S quark plus dilepton, and that automatically implies the reaction, the best reaction below. S quark plus gluon goes to BLL, and this should be anomalous. If the LSCB result is correct, then in the Atlas and CMS and collider experiments, they should be seeing an enhanced rate for this B plus dileptons. So anyway, so I'm going to summarize now. The hints of the lepton universality violation are extremely interesting and intriguing and very important. There is nothing that we know now that says that these hints cannot be true. While these are rather serious, they don't appear to be compelling to me. And in each case, there are issues. For example, the RK star is just one experiment, and G-2 is only one experiment, and we have to wait for Formulab. And one of the issues in all of these is that systematic errors are taken to be in quadrature. And I think in all three experiments, there is no rigorous theorem that you have to justify this. In fact, even in my own experience, I have seen 3 or 4 cases in which, 4 different effects all line up in one direction to cause an effect. Fortunately, the progress will be made both experimental and theoretical in the next couple of years, so that's good. And then, as I said, the third generations, assuming the third generation super partners are the lightest, is RPV becomes a very interesting candidate, and it also gives us stability of Higgs under radiative corrections. We showed 3 benchmark cases, each has 9 parameters and a bunch of masses, and we showed some interesting predictions for the intensity frontier for B and tau decays, the lepton flavor violation, and they are complementary tests in our LHC experiments, and these are being followed. I showed one, and more will come in due course. I'm sorry about the phone. Thank you very much.
Thanks a lot. So any comments or questions from the audience? I do not see any. Okay, so I just wondered because, I missed how, let's say, these would explain the G-2 muon anomaly, in the sense that what is exactly going in the loop? Is there a muon to tau contribution, or there is a supersymmetric particle?
Yes, so the muon goes to third generation B, for example, and
yes, okay.
RPV, there are things like that will happen, There are many graphs, and one of them will be lepton changing to quarks and things like that.
Okay.
So,
can I ask a question?
Sure.
Sony, can you also calculate the case of kaons, not only B, with the same model, the same parameters?
Yeah, this is a very good question. I'm glad you asked. Yes, you can do that. And this is, I was mentioning in one case, in fact, you can ask what happens to K2 pi and epsilon prime and all that. Of course, the setting here is suggest the effects will be smaller, but you know, there is wealth of information, and rather than making a theoretical assumption, one can use that to put better constraints. Unfortunately, it takes time, and our hands are full. And you know, this already took 3 years. So someday, it's a very good question. We are trying to follow it up.
Yeah, I agree. It would be very nice, especially since there are also some Keon experiments running also in the future. So it would be very interesting to have also that predictions. Okay, so maybe we can go on. If you have other comments or questions, of course, as always, please use the Mattermost channel. So now the next talk is by Alexei Sividanov on the tau mu Lepton Flavour universality in Babar.
Hello, do you hear me?
Yes.
Could the previous speaker unshare? Yes, screen. Do you see slides?
Yes.
Okay. Today I will talk about tau mu Lepton Flavour universality in epsilon 3s decays, which was conducted at the Babar experiment. So what you can see here that E plus E minus collision produces off-shell photon, and then it produces a BB bar loop, and then this BB bar loop again goes to off-shell loop, and finally we have final state leptons. And the width of this resonance was known since standard model exception, which is shown here, and so it's very clean and theoretically very well calculated. And so any deviation from this and ratio of those widths into different species of leptons are very well known and free of hadronic uncertainties. So, and any deviation to this ratio from the standard model prediction can give hint about new physics contribution. For example, in this work, you can see that we have light CP-odd Higgs boson, and in this model with large tangent beta, and this A0 boson exclusively decays into tau tau, and thus in presence of new physics, this ratio R tau mu will be enhanced. And also in this work, a new physics contribution to C tau nu, which explains tension in R d star ratio, also necessarily modifies R tau mu or tau e observable. So why we are measuring R tau mu, not R tau e? Here you can see cross section of E plus E minus to mu mu. So you can see that at the peak, it is about 30 times larger than continuum production. However, we have E plus E minus collider, and we have beam energy spread. So, and with beam energy spread, we have this picture here. So it's only 15% larger than continuum production. And similar continuum cross-section for E plus E minus to E plus E minus is more than 500 times larger. So in this case, only dimuon production is possible to extract, or dimuon decays of epsilon 3s is possible to extract. So data for this analysis were collected at the Babar experiment, and the Babar experiment operated at these dates at TEP2 collider at SLAC. And we use data from run 7, about 28 inverse femtobarn on resonance and 2.6 inverse femtobarn of resonance. So, and blind analysis was involved. So only 2.41 inverse femtobarn were used to tune analysis selections and cuts. So, and since you see this off-resonance statistic is slow, we employed also epsilon 4s decays as continuum production for our epsilon 3s measurement, and it has this statistic is much larger, so we do not have problems with statistical uncertainty of background prediction or description. So here you can see signal selections for mu plus mu minus and for tau tau. So they are for mu plus mu minus, they are usual selection to select high momentum collinear particles, and to select muons we have cuts that energy deposition in the colorimeter should be compatible with the muon hypothesis, and at least one particle having IFR response. And with this, we have 99.9% purity. For tau tau selection, it is more tricky because it doesn't have such obvious kinematics in the reconstructed kinematics in colorimeter. So main feature of this analysis is that we require that one particle have to be identified as an electron, and other shouldn't pass or must not pass such electron identification procedure. So it's like electron and not electron. So it suppresses a lot of backgrounds, this condition. And with this, we have 99% purity. And all selections are designed to be beam energy insensitive, since we are trying to employ also epsilon 4s, which is about 300 MeV higher energy. So we performed Monte Carlo selection efficiency correction, which is shown here. So we did this using only off-peak data in off-peak epsilon 3s and off-peak epsilon 4s data. And you can see that this very nice agreement between two data sets, and we can apply such correction. So, and conclusion that this ratio of tau mu candidates does not depend on energy in data and Monte Carlo, so we can safely apply this correction to our own peak analysis. So, and how to separate our continuum production and resonance production of muons. So we can see on this picture that here you can see simulation of epsilon 3s to mu mu, and you can see that radiative tail due to initial state radiation is highly suppressed in these decays. Whereas for continuum production, you see that this radiative tail is much more prominent. And since Babar detector has had excellent momentum resolution, we can exploit this difference in the radiative tail. So, and so you can see in numbers, only 7% are below 3 sigma resolution, and whereas for continuum production, about 23% of events have invariant mass less than 3 sigma resolution. Another background is so-called cascade decays. When epsilon 3s decays, we have decay chain where finally we have epsilon 1s or epsilon 2s, which consecutively decays into a lepton pair. So in this case, you can see that such decays are visible only in dimuon mass distribution. So we can fix amount of such events, and assuming Lepton Flavour universality for epsilon 1s and epsilon 2s decays, we can somehow subtract them from our tau sample. So another background is ISR produced epsilon NS. So we use epsilon 4s data with and this template contains also ISR produced epsilons, so which are shown here. This is our simulation. We used Fakara 10 to estimate this radiative function and subtract such a background from our continuum template histogram. Also, since we use epsilon 4s data, we have also BB-var contribution, which in case of mu dimuon production is negligible, but for tau we calculated possible contribution and applied this correction of 0.4%, which is quite small. So now you can see the fit result to the invariant mass distribution and to measured energy in the detector for tau. And so, minor contribution, as you can see, this is cross-hatch histogram, which corresponds to continuum production of muons and tau. On this picture, you can see already continuum here subtracted, and you can clearly see resonance peak and also cascade decays shown here. And also you can see how well we describe our energy deposition in the detector, measured energy deposition. And the result of the fit shown here, that this ratio number of tau to number of muons is shown here. And this translates to these numbers shown in red. And you can see that statistical error is quite small, less than 1%. So here you can see a result of ISR produced epsilon NS. So on this histogram, you can see that continuum template is not corrected for ISR. And you see this dip here and also this dip here. Whereas with ISR correction, you can see very nice agreement between two plots. So systematic uncertainty estimation is shown on this slide. So mine is a particle identification, and the rest are quite small. And in total, we have 1.4% total uncertainty. So here is a conclusion. So this analysis was done using Babar data collected at epsilon 4s and epsilon 3s resonances. So we set up our selection procedure, which yields finally background level at less than 0.1% for mu and less than 1% for tau sample. We also developed correction to our continuum template to exclude radiatively produced epsilons. And the result is shown here, final result is shown here in red. And this result can be compared with the standard model prediction, which is in blue here, and with the only measurement reported by the CLIO collaboration And you can see that statistical uncertainty is 10 times better than the only previous measurement. Preprint is available. Okay, I'm done.
Okay, thanks a lot. So any comments or questions? I do not see any. Okay, so I try to follow as much as possible. So basically, what is the dominant systematics of your measurement? And I mean, do you have any plan on how to improve it, or it's already?
This is the main
So
systematic uncertainty comes from particle identification. Okay. So, and this particle identification is very hard to improve since it's limit of our knowledge how we will model interaction with the material of the detector.
It's okay. No, I was wondering if, for instance, you can exploit the tau to mu decay, but this is probably too complicated.
Yeah, because already all such tricks already were exploited in this analysis, like all this Babar accumulated knowledge already in this analysis, sure. Let's say.
I guess, yeah. Okay. Thanks a lot. So I don't see any other comments or questions. In case you have some, please use the Mattermost channel. And at this point, thanks again. I would move to the next talk. So Samadrita Mukheri. So, and the talk will be about probing Lepton Flavour violation in minimal supersymmetric standard model.
Yes, can you hear me?
Hello, yes.
Yes, so let me share my screen and here it is. I hope you can see it.
Yes, we can.
So thank you very much. Good morning, good afternoon, and good evening to the people from all over the world. And we will be discussing Lepton Flavour violating decays in MSSM with non-holomorphic soft terms. And this work is done in collaboration with Professor Utpal Chattopadhyay and Professor Debuttam Das, and based on this work. Overviews are outlined in this slide. So let's see how it goes. Among the many models of BSM physics, supersymmetry is a well-celebrated one for many years. And since it solves the hierarchy problem supported by the measurements of gauge coupling strains consistent with precision electric data and Higgs mass, of course. Now, SUSY links different class of particles known as bosons and fermions. Now, it must be badly broken in nature and in general, and SUSY breaking Lagrangian consists of this gaugino mass term, analytic and non-analytic squared mass term, and cubic scalar couplings. Now, MSSM is usually claimed to include all possible soft SUSY breaking terms, that is the terms which split partners, but do not remove the protection against the quadratic divergence to the scalar mass. But however, are there any more possible terms? In a most general framework, it has been shown that certain non-analytic cubic scalar couplings also qualify as soft terms. That is, soft SUSY breaking sector is extended to include this phi square phi star type of interaction. Taking these interactions in the Lagrangian density, we have this q tilde times ht star times au prime u tilde star, and for the down types quarks and leptons and their Hermitian conjugate. Now, these terms are not generally considered because several reasons. Firstly, there is high scale suppression. It comes from the 1/m prefactor here in the order of magnitude of these terms, which can be very large for gravity mediated case as for the CMSSM type of scenario. And another is reappearance of the divergence. what happens in a presence of gauge singlet, which is singlet under the overall gauge group, there can be quadratically large loop corrections depending on the masses of singlet fields. But however, if the mass of singlet field and the chiral supermultiplet is of the same order, then there is no problem. And of course, phenomenological minimal supersymmetric standard model evades these two reasons to not consider these terms. There is no suppression as we are considering all our input parameters in phenomenological scale, and there is no gauge singlet under the SU3 cross SU2 cross U1 gauge group. So there is no question of reappearance of this bad divergence again. Now let us see what happens to the structure of Lepton mass matrices if we consider these phi square terms, that is this trilinear non-holomorphic Lepton mass terms in the mass matrices. We are concerned with the mass matrix in the Lepton sector actually. So the general form of the 6x6 Lepton mass square matrix is given by this, where each element is a 3x3 block. The non-holomorphic trilinear coupling modifies mainly the Lepton left-right mixing. Here we have written the trilinear term explicitly, and as you can see, the term is here a minus mu plus a prime tan beta. In MSSM, it was only a minus mu times tan beta. So both the diagonal one and the off diagonal ones are getting changed by this a prime ij or a prime ii type of interactions. So our analysis, however, only explored these non-diagonal holomorphic and non-diagonal non-holomorphic trilinear couplings to study the Lepton Flavour violating observables. So what do we know about the Lepton Flavour violation? The observation of oscillation between neutrino flavor eigenstates implies that Lepton family quantum numbers are not considered. And as a consequence, one can also explain the flavor violation in transition between charged leptons. However, charged lepton flavor violation has never been observed in any experiment, which would have been a clear signature of the beyond standard model physics. Null results from these experiments indeed constrain respective model parameters. And tremendous effort is currently being realized to achieve unparalleled sensitivity to probe Lepton Flavour violating decays at like Meg, Bell, Baber, LHCb, and at all other experimental facilities what is happening all over the world. Now we will see that we know that absence of any flavor changing neutral currents significantly constrain the non-diagonal elements. But charge and color breaking minima aspects are more robust in this aspect. Now, in the Lepton sector, there is no color breaking contest, so we will study the charge breaking minima here. In a theory with multiple scalars, choice of desired electroic one puts restriction on the allowed parameter space. The total tree-level potential is given by this equation involving Higgs, electrons, muons, tau. Coefficient A, B, C for two cases are here. Please note the presence of both diagonal and the off-diagonal trilinear couplings in both cases. Now, considering all the three generations, the condition to avoid any charge breaking minima is derived as follows. For the first one is for the holomorphic trilinear couplings. Note the presence of Aij here and the corresponding off diagonal Yukawa coupling element, and the one with non-holomorphic and holomorphic one is given by here. So Aij minus Aij prime mu times Oiij is present. So in, okay, I will hurry up. So in, as I have 5 minutes more. So here in our numerical analysis, we will consider this bilinear soft Lepton mass matrices element to be exactly equal to 0. So whatever be the flavor violation, that will be due to the Aij and Aij primes. So let us see how the results comes out to be. Flavor violating Higgs decays play a significant role for investigating lepton flavor violation. The effective Lagrangian phi LILJ vertex has three parts. The first term denotes the Yukawa interaction, where epsilon1 encodes the correction to the charge lepton Yukawa coupling from flavor conserving loops, and the last term corresponds to the source of flavor violation. And epsilon1 and epsilon2 arise out of loop function involving neutralino and leptons. This effective Lagrangian essentially generates all the off-diagonal Yukawa couplings radiatively in the respective trilinear coupling is non-zero. Now, strengths of physical Higgs boson to the leptons are given here with kappa ij factor. Typically, dominant contribution come from the CP even heavy Higgs and CP odd heavy Higgs, which are evident from the factors in front of them. That is sin alpha minus beta in the decoupling limit, it is close to 1, and for CP odd heavy Higgs, it is 1. The scatter plot shows the branching ratio H to mu tau and H to E tau as a function of Aij in cyan and Aij prime in blue, respectively. An appropriate non-holomorphic coupling, that is in the blue, additionally multiplies with tan square beta, leading to an enhancement by a factor of 10 to the power 3 compared to the MSSM values. As mentioned earlier, the heavier Higgs are dominant one in the LFB decays for decoupling limit. Spread of the branching ratios as shown for 1.5 TeV heavy Higgs mass. All points here satisfy the upper mass bounds for various masses which have been searching in the LHC, the various LFB decays like mu2 E gamma, mu2 3 and other flavor constraints and mass bounds from LHC, and of course avoid deeper charge breaking minima than the electroweak one. Now, with the identical Yukawa couplings that MSSM inherits from standard model, we will use constraints of LHC from on relevant off-diagonal Yukawas to restrict the trilinear parameters. To draw these bounds, we need to fix the neutralino and lepton mass at some fixed values. Clearly, the larger radiative correction are induced in case of Aij particularly, as it is seen from the right column. And the left panel is for holomorphic and right panel is for non-holomorphic trilinear couplings. The black horizontal line in each plot relates to the upper bound on root over Yij square plus Yji square, as can be seen here. And for first generation, it is coming from the mu2 E gamma limit, and for first, third and second, third generation, it is coming from the LHC 13 TeV data. And here you can see the extent of variation due to the non-holomorphic couplings is much more larger. Actually, it is 10 to the power 3 times larger. Now, with the understanding on how off-diagonal Yukawa couplings can directly influence the free rise of trilinear coupling, we have shown here the bounds in the mod Yij times mod Yji plane. And here the different light and deep red shades region are restricted by the upper bounds of flavor violating LFB decays. Again, it is shown that for first two generation, mu2 E gamma is the most constraining one. And for the other two generation, it is the CMS and Atlas 13 TeV data. Blue points are derived from the non-holomorphic couplings. And as you can see, it is the large extent of non-holomorphic couplings are excluded from the search of the LHC and null results from the mu2 E gamma. So let us wrap up quickly. For most of the charge lepton flavor violating observable, the standard trilinear coupling A, that is the holomorphic one, turn out to be inadequate to produce any significant result for the present or even the future sensitivities. So we have two classes of non-holomorphic coupling. One of them is Aij prime, may imprint significant contribution in these processes. A reasonable amount of off-diagonal couplings together with the diagonal one may lead to potentially dangerous charge breaking minima, and we derive the condition analytically to preserve the global minima, which is charge conserved. And non-holomorphic coupling is always better suited in achieving large rates than compared to the holomorphic couplings. And as we discussed from the results, that mu2 E gamma constraint is more favorable to test Aij prime for the first two generation, and the LHC limits are more favorable to test the second, third and first, third generation of diagonal couplings. So with this, let me thank you all for your attention. So that's it.
Okay, thanks a lot. Any comments or questions from the audience? I do not see any. So I just wanted to ask you. So I've seen you are mostly discussing about lepton to lepton gamma decay or to the Higgs to lepton lepton. But do you think that, I mean, is there any let's say possible constraint coming from the meson let's say lepton flavor violating decays, or it was just not considered? I mean, is it sensitive, not sensitive, or was just not considered?
Okay, we have not studied these mesons to lepton flavor violating decay in this analysis, but I think it will be sensitive because we have considered this lepton left-right mixing, and for quark sector also we can have the non-holomorphic of diagonal elements. So meson containing like UD bar or some K mesons, etc. Then if we consider the non-diagonal couplings non-holomorphic in the quark sector, then we can have some imprints of them in that decays also. That may be a study. We can have their imprints.
So it also can occur there. Okay, very nice. Okay, thanks a lot. So if there are no other comments or questions, I thank you again. And I would move to the last talk of this session before the coffee break. And we have met Yusel about the mu2e experiment.
Hi. I will share now.
Yes, please.
And then I'll start the presentation. Can you see this? Yes, okay. So I'm going to talk about the mu2e experiment at Fermilab, our motivation, the design of the experiment, and I'm going to report on the progress. So we'll start with what is a charged lepton flavor violation. We know that quarks mix, but why don't leptons is the actual question. So as discussed in other talks today, the charged lepton flavor is not conserved, as indicated by neutrino masses. So let's use that, and let's look at a process which is mu2e gamma and in the standard model, and calculate the branching ratio. That turns out to be 10 to the minus 54, which is heavily suppressed. So that means if you point something here, it will indicate into new physics. So here I list some newer experiments focusing on the muon sector. And of course, we're going to talk about mu2e, which is the neutrinoless conversion of the muon. So which scales mu2e probes? Here's our effective Lagrangian. Here is the lambda is the mass term, and the kappa is a scale factor between the first and the second terms of this Lagrangian. So if the kappa is low, you get effects sensitive from the loop contributions to the Lagrangian, as indicated here. These can be supersymmetric model, heavy neutrinos, and all those things. And if you increase the kappa, then your second term dominates, and this is sensitive to what we so-called contact term, and these couplings interactions. So why is mu2e unique? So let's try to understand that by looking at this picture, the plot of kappa versus the mass scale. Here you can see the mass scale mu2e probes. Let's start with syndrome 2, which is the older experiment. This puts our limit at conversion limit at 10 to the minus 13 and covers this region of the spectrum. And we have mu2e gamma experiment, again at 10 to the minus 13, covering this sector. So in comparison, mu2e can probe up to 10 to the 4 TeV. And not only that, in comparison to collider experiment, mu2e is free from standard model backgrounds. You can also have intense muon beams for high statistic, which you can't get in a general collider experiment. So let's look at our signal, the coherent electron conversion with the aluminum. Here you can see a muon going in orbit around the aluminum. So it will lose some energy when it converts the electron to some to the binding and some to the nuclear recoil. So you put that in and you can calculate this monoenergetic electron of 105 MeV. So what we're looking for is the rate of this conversion divided by all the other captures. And this will give you your conversion rate, which we aim 3 times 10 to the minus 17. And this will be a 10 to the 4 improvement over syndrome 2, the last experiment. So let's talk about our backgrounds. The biggest background we have is decay in orbit electrons. Here again, the same picture, muon goes in around the aluminum. It's this time regularly decays into an electron with neutrinos, which then shares the momentum with the electron. This means it has a lower energy peak compared to our muon mass. So this spectrum, let's inspect the tail end of it. It decreases sharply. So if we plot our conversion electrons on top of this decay, the background will get this. So the METEOR experiment tries to separate this red signal from the blue background. And to get that, we need a good momentum resolution. So let's summarize our design principles. So we want to get 10 to the 4 improvement over the last experiment. The question is how to get there. So firstly, we get there by having a high intensity pulsed muon beam. This provides you with high statistics, but also with the beam, it introduces beam backgrounds. So what are those? Like pions and muons coming with the beam and then decaying in flight, radiative pion capture or antiproton annihilation. These are some examples. Secondly, we need high resolution on the momentum to be able to separate 105 MeV conversion electrons from the DIOs. To achieve this, we have a tracker, an electromagnetic colorimeter. And then to get a discovery, we need a background suppression of less than 1 event for the whole experiment. So that means making the detector basically blind to lower energy particles. We're going to use an event window separation with pulsed muon beam. And we need a way to veto cosmic rays because they're also a big part of the background. They produce 1 conversion-like electron per day. To the discovery we need 99.99 veto efficiency, which is really hard. So let's talk about our live event window. Our 8 GeV pulsed proton beam comes to the target at 1695 nanosecond intervals. We wait 700 nanoseconds before we take any conversion data. So this allows for all that prompt background that comes with the beam to die out even before we start taking beam data. So here's an example, radiative pion capture, one of the biggest. Pion is captured by the aluminum, releases a gamma, which then converts into an electron and positron pair. Here you can see that it just dies out while we're taking signal 700 nanoseconds later. You can ask, what about out-of-time protons? Well, out-of-time protons per beam, we limit that to 10 to the minus 10. So here's an overall picture of the experiment. It has 3 superconducting magnets. There's a production solenoid. 8 GeV proton beam comes here and hits the production target housed in the production solenoid, which produces muons. We direct them to the transport solenoid where they transfer into the muon stopping target. So this transport solenoid has an S-shaped geometry which selects low momentum and negatively charged particles. And then these go into the detector solenoid. The conversion electrons go into a helical orbit, hitting the tracker and the colorimeter. So all of that is covered by our cosmic ray veto system. Here you can see these are like giant scintillators. Here you can see that it is covering the whole of the detector solenoid and some part of the transport solenoid. So our progress on the solenoids, here is a picture of the muon beamline showing where different parts of the solenoids are at. I would say the transport solenoid is the farthest one apart in terms of completion. So let's talk about the tracker, which I work on. This is the main detection element of MUTE. It's a low mass tracker using straw drift tubes running argon CO2. Here's a picture of the straw, 5 millimeter in diameter. We have a 96 per tracker panel staged in double layer configuration like this. Here's a panel. We put 6 of them together to produce a plane, and the whole tracker consists of 36 such planes, and it is 3 meters in length. This highly segmented nature of the tracker helped with the particle identification, and our momentum resolution hits our design goal of 180 kF. So our progress, the tracker panels are produced in the University of Minnesota. 40 out of 216 are produced. In comparison, planes are going to be produced at Fermilab. We did a trial at back in February before quarantine. Now we're planning to do a vertical slice test, which is a complete test of tracker plane with the production electronics. And this is going to be done in September. Here's an example of the tracker construction. Panel upside down, particle comes down, and then you can see that it hits both layers. And we calculate, we determine the distance of closest approach on each straw to construct a track. So let's switch to electromagnetic calorimeter. We have 1,348 cesium iodine crystals. These are all read out by silicon photomultipliers. The design is similar to tracker with this annular structure with a hole in the middle. Here you can see a prototype from 2017, which achieved all the experiment's goals, like the time resolution, energy resolution, and spatial resolution. So the progress on calorimeter, we have cesium iodide crystals expected to be done by August. They're measured at Caltech for light yield and resolution. All the systems are completed and assembled into these plates, which will be then installed into the calorimeter. A cosmic ray veto, we talked about this. It consists of these polystyrene scintillators layered in this 4-layered staging. And it covers all of the detector solenoid. Whenever a particle, a muon passes by, we do a coincidence of 3 out of 4 and eliminate the cosmic muon. So the progress, all of the SIPM, 8% of the SIPMs are tested. The die counters, 58% of them produced. Then they're being assembled into modules. Here you can see a picture of a vertical one. And here you can see a side one. And 20 out of 83, 24% is completed. So all of that design and detector elements combine into this background summary table, which lists intrinsic, this prompt, beam-related prompt, and the cosmic ray backgrounds. And in total, we achieved 4.41 event per the experiment lifetime. So let's talk about our sensitivity. So this is what we want to find. To get the 5 sigma discovery, we need our mu-TE 2 times 10 to the minus 16. If we have, if the conversion is above that, we get 5 sigma discovery with 90% confidence level for the exclusion at 8 times 10 to the minus 17. This interestingly means to get this, we only need 7 conversion electrons. So in summary, mu-TE will improve current limit on conversion rate by 10 to the 4 at the single electron sensitivity of 3 times 10 to the minus 17. It will probe mass scales up to 10 to the 4 TeV. Our current schedule is the installation and commissioning starting in 2021, the physics in 2024. This means 1,000 times improvement over the current limit by 2025. Then there's going to be a shutdown, and we will then, by the end of the decade, hopefully get a 10,000 improvement over the current limit. And the next 2-3 years, we'll see a big effort on building and commissioning the detector. So thanks for listening. Here's a nice picture of Fermilab campus with a mu-TE building in the lower left corner. So that's all.
Okay, thanks a lot. Any comments or questions from the audience?
Hi, thank you for a good talk. I have two questions.
Yeah.
So one is that if there is any plans for upgrade or something else during the PIP2 shutdown. And next question is that if there was any chance to measure the extinction directly.
So for the first one, let's do. So yeah, so there's an upgrade already planned, MUTE2. The schedule is not solid yet, but this of course uses the PIP2 beamline to get a better beam for the experiment, which in then increases our resolution. Of course, this has to come with like all the upgrades to the tracker and the solenoids and or the improved CRV. So the studies are currently being done on how to upgrade those for the next generation, but it is planned. What was the second one? Your
the second question was if there was any chance to measure the beam extinction directly.
Yeah, so not here on my slides, but we have an extinction monitor. Let's go here to get a picture of the experiment. Yeah, so right around here, before the beam comes to the production solenoid, we have an extinction monitor, which measures this out-of-time particles and then and collimators that limits that number to 10 to the minus 10.
Okay, thank you.
You're welcome.
Okay, thanks a lot. I don't see any other comments or questions, and in case there are, please use the Mattermost channel. At this point, I would propose to go on with the coffee break, and I leave the chair to Carla. So please, Carla, tell us when to reconvene.
I'm sorry, I wasn't able to unmute. So we reconvene here at we are on time, so at 7:08.
Okay, thanks a lot.
If someone wants to test the slides in this 3 minutes.
Carla, could I please?
Yes, sure. Try to pass it. Yeah, okay, great.
It's working? Great, okay.
Yes.
I will stop so someone else can.
Okay, anyone else?
Yes, I vote this. Okay, someone else before. I will test later.
Okay, and just share. Can you see them?
Yes.
Okay.
Great. Next.
Yes, that will be me. 1 second. Can you see them?
Perfect. Yeah.
Great.
Can I also try?
Anyone? Try. Yes, sure.
Can I try?
Just a moment. Eva, I can't see yours on full screen. Yeah, I can see that way. Maybe you just use from there. Can I try to speak? Eva?
Sorry. Yes. Yes.
Okay. Just to test.
Yeah.
So anyone else?
I'll stop sharing now.
Yeah, probably you need to pass from there. I couldn't see the other way. We can try later, but just
Yeah.
be...
No. I'll just keep it like that.
Okay. Can you stop sharing? Okay, I just stopped for you. Well, it's time to restart, so. Otherwise we won't be able to be on time. So we are resuming the last block this evening of the session 2 of the Quark and Lepton Flavour Physics. We'll have 7 talks on CP violation from Atlas, CMS, and LHCb, and the last talk from the Dipole B project. So we start with Sneha from the with time integrated measurements of angle. Please go ahead.
So good evening. I will be telling you about our latest measurements of the CKM angle gamma from the LHCb experiment. So we know that the standard model is not the full story. There are empirical and aesthetic reasons to expect there to be physics beyond the standard model. A promising area that we can explore to try and look for the effects of new physics is CP violation. Within the standard model, the CP violation in the quark sector is encoded within the CKM matrix, which describes the coupling of the weak and the mass eigenstates of quarks. Using the properties of the unitary matrix, we can represent that matrix as a unitary triangle, and the angle gamma is of particular interest at the moment. So gamma is interesting because it's the only angle which is easily accessible in processes that only include tree-level decays. Tree-level decays basically mean that they are standard model benchmarks because it's very difficult for new physics to interfere and change the values. Also, with gamma, we have effectively no theory uncertainties. So how do you go from a standard model benchmark to new physics? Well, you can also make indirect determinations of gamma. So here one assumes that the triangle is closed, and we make measurements of the other sides and we use measurements of the other sides and angles to infer the value of gamma. Here, new physics is more likely to contribute because a lot of these processes have loop decays in them. And so there is a potential for a different central value. If we take a look at the current values, we see that the direct measurements and indirect measurements are a little bit different. It used to be about 2 sigma different. That's a bit less so now. But nonetheless, the uncertainties on the direct measurements of gamma are still very large. And significant progress is possible in the next few years. And that's one of the reasons why this is so interesting at this point in time. So time-independent measurements of gamma are typically made in B to DK decays. There's a favored decay and a suppressed decay. And the amplitude ratio between them is RB is dependent on some hadronic parameters from the strong interaction, RB and delta B, and then the weak phase, which is the one that we're interested in. Now, in order to access the phase gamma, we need to have a system that has interference, which means that we need to have the D0 and the D0 bar mesons decay into the same final state so that we can have access to the phase from the interference. The level of interference and its exact manifestation is going to be dependent on the physics of the B decay, but also of the D decay. The measurements I will be telling you about today will mainly be our new result, shown here for the first time on B to DK, where D goes to K short pi pi or K short KK. I will briefly show you the results from a similar analysis where the D decays to K short K pi. And Ava will tell you about some of our time-dependent results in the next talk. So if we take a look at our data collection for B to DK and B to D pi, this is our full data set from 2011 through to 2018. We can see that the excellent detector performance has given us great, it's given us great performance here. So we have very large yields, so 15,000 B to DK and 210,000 B to D pi. And this is a result of having excellent hadronic trigger efficiency. The IP resolution that we have means that we can really beat down those combinatorial backgrounds. And the momentum resolution means that we can separate this partially reconstructed background on the left-hand side from the signal very well. And finally, our hadron PID means that we can select out B to DK very cleanly from B to D pi, which has 12 times the branching fraction. So if we were interested to see what CP violation would look like, we would take a look then at the Darlitz plots of the D decay from B plus and B minus decays. You can see that already with the statistics that we have, these differences are visible by eye. So for example, if you take a look at the red circle, you will see that the points in the left-hand plot are more concentrated than the ones on the right-hand side. And the magnitude and position of these differences is driven by the values of gamma and also these other hadronic parameters. So the idea of the analysis is quite simple. We just want to compare the bin yields between B plus and B minus decays. We don't use a standard rectangular binning because we know that this is likely to dilute our statistical sensitivity. So we use these highly non-uniform binning schemes for K short pi pi, and we can also add K short KK. And these have been designed to maximize our statistical sensitivity. The key point here is that the results are independent of any amplitude model. And this means that we don't have to worry about how we are assigning our systematic uncertainties, which is important when it comes to precision measurements. So we can compare the yields to a number of parameters. So the equation looks complicated, but it boils down to these X and Y parameters, which are our physics parameters of interest, and they basically parameterize the real and imaginary parts of the amplitude, and they have the sensitivity to gamma. We then have the CI and SI, which are essentially strong phase parameter measurements of the D decay. So this is the information that we need about the D decay. It comes from BESS3 and CLIO. And the reason why it has to come from another experiment is that we need a system that can access these parameters. And one of those systems are quantum correlated D decays from the psi double prime. And finally, we have these F parameters, and this is just the fraction of the pure D0 decay into a given bin, taking into account reconstruction and selection efficiency. One of the key parts of the analysis is attaining these FI to measure them. We know that our efficiency profile is not uniform at LHCb, and previously we've used B to D star mu nu as a control mode to determine the FI. But the trigger and the selection can't be the same, and it was becoming clear that we would be leading for very large systematic uncertainties if we continued to follow the same path. Ideally, the best control mode would be B to D pi. It has the same efficiency because the topology is the same and we can apply the same selection. Also, the branching fraction is 12 times larger than B to DK, so there are enough statistics there to control. But it had always been a worry that the CP violation in the decay mode and other physics effects in this channel may make may be problematic in the actual execution of the analysis. However, we've understood these physics effects much better now, and we also know how to take into account the CP violation. And so for the first time, we use this as a control mode to determine the FI and simultaneously determine the CP violation parameters in B to D pi. So we perform a fit, which is essentially the fit to the invariant mass model, the invariant mass spectrum in each bin separate, simultaneously, and we use that to determine the X and Y CP observables. What I've shown here is bin +4, which is one that exhibits a large amount of asymmetry. If we take a look at the results, we can plot X and Y. And the signature for CP violation is that these two blobs are separated. And so you can see that they clearly are separated. And if we take a look at the bin by bin pair asymmetries, you can see that we do in B to DK see some very large asymmetries and that the fit predictions match the data very well. On B to D pi, the CP violation is expected to be an order of magnitude smaller. So the asymmetries that we're expecting are much smaller. And for this reason, the data is not yet sufficient to be able to say that we can see CP violation in this decay mode. We can compute the value of gamma from these CP observables. And so we measure gamma to be 69 plus or minus 5 degrees. That is nearly all. That is dominated by the statistical component, which is about 5 degrees. And then we have two sources of, we have two classes of systematic uncertainty. One comes from the propagation of the uncertainty on the strong phases, which are the measurements from BESS3 and CLIO, and you can see that they have an uncertainty of around 1 degree. And then we have a number of systematic uncertainties from the experimental side on LHCb, and these add up to about 1 degree as well. We can compare that to our previous measurement that used 2011 to 2016 data, and you can see that this is a substantial improvement. We've gained in statistical uncertainty by adding the 2 years of data and some small improvements to the selection. But one of the key points here is that the old uncertainty from CLIO, which was about 4 degrees, is now shrunk to about 1. And this is and you can imagine that if we still had a 4 degree uncertainty, we would, there is no way we could reach a precision of 5 degrees. And so these new inputs from BESS3 have made a big difference. And then secondly, we've been able to very much reduce the systematic uncertainties from the experiment by using this B to D pi mode as the control. We also measure a number of hadronic parameters, and the B to D pi hadronic parameters are measured for the first time, and they will have impact when they go into the full gamma combination. The measurement of gamma reaches a similar position as all other measurements of gamma combined. As I said, we have a large number of B and D decays are being pursued at LHCb to measure gamma, and there is a large amount of current activity to update these to the full data sample, or even introduce new methods. I show here another decay mode, which is B to D K, where D goes to K short K pi. Again, asymmetries are visible in these decay modes. This is as a standalone measurement, this doesn't have direct sensitivity. It can't make a measurement of gamma on its own, but it does contribute to a combined measurement of gamma, which will be put into the next combination. So to summarize, LHCb have started to release full run 1 and run 2 measurements of gamma. We have a new result, which has a precision of about 5 degrees, and it's the most precise measurement from a single measurement. And we have benefited from new control modes and new external inputs of strong phases. If we take a look at how the LHCb combination looked in 2018, you can see that once these measurements are added to it, the LHCb is well on track to surpass the 4 degree 1 plus root 1 2 target. And so we put ourselves in a very good place for the upcoming upgrade. Thank you very much.
Thank you, Sneha. Questions from the audience? I don't see any. So I think we just continue with Eva Gessebeck with the time-dependent measurements from B to D in LHCb.
Thank you. Can you see my screen now?
Not yet. Yes, now I can.
Okay, thank you very much for the introduction. So what I'll speak about now is pretty much complementary to what Sneha presented. I'll be speaking about the time-dependent beauty to open charm analysis we do at LHCb. We're interested in them because they are sensitive to the weak phases beta and gamma and beta S, and we do them in a time-dependent way when we deal with neutral B mesons. This we do in order to resolve the B meson oscillations, and to do that we fit for the decay time dependent decay rates, and we extract the parameters of interest. So these measurements also require knowledge of the external parameters, gamma, delta M, and a few others you will see in the slides thereafter. And to check for further updates on these charm final states at LHCb, you can check the talk by Wojtek tomorrow in this session. I'll start with the B0 to D star D decays, where D star and D are charged. And this is the first measurement we do in these decays at LHCb. It's been done previously by Bell and Babar. Here we're dealing with B2CC D-bar transition, where we have 3 penguin exchange and annihilation diagrams. Therefore, in addition to the mixing-induced CP violation, we also expect possible direct CP violation contributions. And in the little sketch in the corner, you see the possible decays of the B0 and the B0 bar decays. They are all accessible from all states. In addition to that, you have the B0 bar oscillation. Therefore, we're sensitive to CP violation, as I said, in the interference and also the direct one. On these slides, you see the time-dependent decay rates. I've highlighted with yellow the external coefficients we used, the decay time and delta M, and I've underlined with purple the CP coefficients, which are of interest to this analysis. And you see the definition also of these coefficients using the H-fluff convention and their relation to the, for instance, lambda f, the CP parameter, and overall the overall asymmetry between the F and FF bar final states. So the one CP coefficient which is of most interest to us in this case is the S d star d, which if we assume that we can neglect the penguin contributions, which are known to be about a few percent, and we can essentially assume there is no direct CP violation. If we can assume that, then the S d star d would be a good approximation of the sine 2 beta, which is the angle of the unitary triangle. So for this analysis, we used the full sample of run 1 and run 2, which is about 9 inverse time to Born. And here we split our data into 4 subsamples according to the decay of our intermediate the zero Mason, and according to the LHC run. And we fit that. You see on the left plot the fit to the invariant mass of one of those 4 subsamples. And then we fit simultaneously all the 4 subsamples, and we perform a decay time fit. We use about a total of 6,000 candidates to measure the CP coefficients of interest. On the plot on the right, you see the asymmetry between B0 and B0 bar decays. And actually on this slide, you see the results for all 5 coefficients. And this is the most precise measurement of CP violation in this decay channel to date. This is a relatively new result. The publication went out this spring. The hypothesis of CP conservation is excluded with the great significance in these decay channels. What you note here is that the coefficient C and the coefficient A are compatible with 0. Therefore, this indicates no CP violation in the decay. And then we can make this assumption that there is no direct CP violation. We can fix them to 0 and we can repeat the fit, and then we get a value for sine 2 beta, which you see here, and this is about 1.9 sigma away from the world average. Okay, I'll move to the next decay I'll discuss. This is the second out of 3 time-dependent measurements. So here we have neutral B0 going to charged d meson and the pion decays. The 2 leading Feynman diagrams contributing to the interference in this decay channel you see below. We have a transition of B2CW and another one of B2UW. This is analogous to the last decay I'll discuss later, BS to DSK decays. So I mentioned we have an interference between them, and the weak phase difference between these is gamma plus 2 times beta. Again, we have the time-dependent decay rates with the external inputs and the CP coefficients CF and SF. Those CP coefficients are expressed with this is the relation basically to the ratio RTP to the strong phase delta and to the weak phases beta plus 2 times beta plus gamma. For the coefficient CF, we can set it to 1 because we know that the magnitude of RTP is quite small, it's below 2%. So, thank you. We basically effectively remove this out of the equation and we set it to 1. RDP would also be used in the other as an input, and we can constrain that from the bar and bell. 2 times beta, we would constrain from the H-fluff. Therefore, we extract the values of SF and SF bar from a multidimensional fit. One of the components One of the fits we perform is to the invariant d pi mass, which you see on the top plot. We have a very, very clean peak, very significant. The data, we have close to 500,000 events. And you see our results for SF and SF bar using our run1 sample. And then we use these CP coefficients to constrain further the strong phase delta and gamma. And you see the intervals, the confidence intervals for these variables, delta and gamma, and also the two-dimensional scan at the bottom plot of delta versus gamma. As I mentioned, we need the RDP as an input. We are able to calculate it. And for the analysis I just presented, that's been done using information from the PDG, using measurements of Bell and Babar. But we can also measure it at LHCb, and we're doing it using B0 to DS pi decays. We can do that because we have a clean hedronic 3 decay. You see the Feynman diagram here in the upper corner. And the branching ratio of these decays is interesting because it's proportional to the CKM element VUB and also to some non-factorizable strong interaction effects in B2U decays. However, what's most interesting for us in this case is that we can use this branching fraction to calculate RDP using the second formula on this slide here. And here it's how this branching fraction enters. So using 5 inverse femto barn run1 plus part of our run2 data, we're able to measure this branching fraction and RDP. This is a new result, which is also preliminary, and Wojtek would discuss it in more detail tomorrow. And here we have the best precision in this decays in agreement with the world average. Okay, I'm at the last time-dependent measurement I would discuss. This is the measurement of the CKM angle gamma with BS to DSK decays. This is very well known. Here, essentially, we have a similar situation. We have two leading diagrams with transitions of the B2CW and B2UW. So here, in contrast to the B0 to D pi decays, we have two amplitudes that are both proportional to the amplitudes are of the order of lambda to the power of to the third power. And here we have the weak phase difference of gamma minus 2 times beta, analogous to the gamma minus 2 beta. So beta S we take from other external measurements. And if you're interested, check out the talk of Pei and Lee on the recent BS measurements with the LHCb experiment. Again, we have a time-dependent decay rate with external inputs and the CP coefficients. You see their relation to the, to the strong phases and the weak phases and the ratio RTSK. Here is what we determine with our run1 data sample, and using that we can actually also plot the asymmetries. Shown here above. We can also interpret these variables in terms of RDSK, delta and gamma. You see the two-dimensional scans of RDSK and gamma, the strong phase versus gamma, and then the single measurement of gamma, which is at about 128 degrees, which is very nice. Then we use those as input to the combination of gamma, and Matt Kenzie has shown this plot at FPCP. So here the BS contribution is in red, and you see it's a bit far away from the results with using B plus and B0 decays, B plus being the results that Snea just discussed, and probably this would be updated now after the results that Snea updated. So there is a certain tension. We are very curious to understand where we have this tension from. And I arrive at my summary and conclusions. I've presented 3 time-dependent measurements at LHCb. They are sensitive to the CKM angles 2 times beta and gamma. We've done some future projections, what we can do with 50 and 300 inverse femtobarn at LHCb. And probably if there is one number to take from this slide, this is that with the LHCb upgrade 2, we can reach a precision of about 1 degree with DSK decays, which is very nice. We're also working towards finishing our run 2 analysis and adding a new decay channels such as the BS to DS K-pi or some new states, including excited D and D star modes. So hopefully this will be available soon. Okay, that's all from me.
Thank you, Eva. Questions from the audience? I don't see any. Please don't forget to use the Mattermost channel so you can, if any question arises later, the discussions proceeds there.
Thank you.
Thank you. So we can move to the next 2 talks on PHI-S. The first from Atlas, results on PHI-S from Thomas Jacobbeck.
Yes, hello, do you hear me?
Not so loud.
Okay, give me a second. It's better?
It's better now, yes.
Okay, so do you see my slides?
Yes.
Okay, great. Thank you very much. Hello, everyone. Good afternoon. So yes, I'm Tomáš Jakóbek. It's Czech name, so I'm almost here in this conference. So on behalf of the Atlas collaboration, I'd like to show you the latest or the updated results of our measurement of CPA violation in the BS2 J-Psi-Phi decay channel. So this channel is expected to be sensitive to new physics contributions to CP violation, and it's often called golden channel by the community. Before the decay, the B meson can oscillate into its antiparticle, and this oscillation can be characterized by the mass difference between heavy and light mass eigenstates. If in the absence of the CP violation, these states would then correspond to the Flavour eigenstates. So in general, we define 2 types of CP violation in decay, where the amplitude of meson to the final state is different from the decay amplitude of an anti-meson to anti-final state. Then there is a violation in mixing. In other words, there's asymmetry in the particle-antiparticle oscillation. And these 2 processes or these 2 types of violation can interfere. And so we define CP violation in the interference of mixing and decay. This one is only possible if meson and its anti-meson decay in the same to the same final state. In other words, the oscillation can occur before the decay. This is of course the case of the BS2 J-Psi-Phi decay channel. So what defined the CPA violation in this channel is a weak phase difference between the mixing amplitude and B to C bar S transition amplitude. In the standard model, this phase can be related to the Kawibo-Kobayashi-Maskawa quark mixing matrix, and thus can be predicted very precisely to be minus 0.037, let's say. So any sizable deviation would be a clear sign of beyond standard model physics, because these processes would then introduce contribution or contributions to the box diagrams describing the BS mixing. So to our measurement in Atlas, so it was done using the data collected by the Atlas detector, of course. This is one of the multi-purpose detectors on the LHC. From all the important parts, let me mention the muon spectrum is used for triggering the data we use for analysis, and the inner detector, which is used for precise tracking. New innermost part was inserted before run 2. We call it an insertable B layer. And thanks to this layer, we have much better mass and lifetime resolution. For triggering, the physics rely heavily on low PT muons, and the yields of our typical dimuon triggers with invariant mass windows are shown on the right plot. Basically, all our triggers are 4 or 6 GeV dimuon triggers. Our analysis started many years ago. The first paper was based on 5 inverse femtobarns of 70 EV data. Then we've published the full round 1 analysis with additional 14 inverse femtobarns of 80 EV data. And today I'd like to show you the latest result and its update. It's our partial run 2 analysis using 80 inverse femtobarns of 13 TeV data from years 2015, 16, and 17. So without the last year of data taking. In our analysis, we require at least 4 tracks in the event, 2 muons and 2 other tracks. We do not have any particle identification atlas, but because of the muon spectrometer, we can of course exclude muon tracks from the set. Then we refit the vertex, or then we refit these 4 tracks to the common vertex under the K-on-K-on hypothesis for the remaining tracks. And by refitting these 4 tracks, we can then obtain a secondary vertex and a decay length or a lifetime of the B particle, B meson. If it happens that there are multiple BS candidates in the event, then we take the one with the best vertex fit. All signal background separation is then done completely by an unbinned maximum likelihood fit. So BS to JPSI-Phi is a decay of pseudoscalar to vector-vector final state, which is thus an admixture of CP odd and CP even states. We can distinguish these states through time-dependent angular analysis, but our data are still polluted by non-resonant S-wave decay BS to JPSI K plus K minus, and also by the decay BS to JPSI F0. Unfortunately, these events can be identified in the data and thus can significantly bias the measurement of the weak phase. They also interfere with the signal decay, so we have to include them in the differential decay rate, and everything is then treated by the fit. So a few words about the flavor tagging, which is of course very important in every CP violation measurement. We use so-called opposite side tagging, where we try to deduce the flavor of the signal B meson from the flavor of the other B meson produced in the event. For calibration and performance estimation, we use a self-tagging channel, B plus minus to JPSI, K plus or minus, where the flavor of the B meson is given by the K-on charge. To identify, so to identify the flavor, we use Lepton tagging, where it's this is based on the semi-leptonic decay of B meson, where the flavor is given by the lepton charge, but of course it's diluted by the B to C quark transition as well as oscillation itself. This fact can be improved by the moment weight charge of the lepton and tracks in the cone around the leading lepton. If there is no additional muon or electron in the event, we try to use BJ charge tagging. We calculate the momentum weighted track charge in the jet. From the calibration B plus to minus sample, we then map these charges to a probability that the given candidate is BS or anti-BS, and this probability is then used in the fit on the per candidate basis. If there is no tagging information, we assign a probability 0.5. In this way, we can tag we can take about 15% of all BS candidates. yeah, so you can see the comparison of our tagging methods and also the mapping from the charge to probability on the bottom plots as an example. So to obtain the physics parameter in decay, we used an maximum likelihood fit, which takes all possible information about the event, so the mass and its uncertainty, proper decay time, angles between final state particles, BS momentum, and the tag probability. And the fit then determines 9 physics variables: the weak phase, decay width of heavy and light mass eigenstates, and 3 amplitudes and relevant strong phases. So the likelihood function consists of 4 main parts: the signal part, 2 specific backgrounds from misreconstructed BD and lambda BD decays, lambda B decays, and combinatorial background. And then all of these probability density functions are weighted for the proper decay time efficiency. Here you can see the fit results of our partial run-to data analysis. This is a fit projection to all data passing this passing selection. The ratio plots below each figure include both statistical and systematical uncertainties, and you can see that these plots cover all the differences between the data and the model. During the analysis of the full run-to dataset, we observed there is a secondary minimum with respect to the 2 variables, 2 observables. It's a delta parallel and delta perpendicular. We have both solutions here. The origin is an approximate symmetry in the signal in the signal probability density function, and we measure the two solutions has difference of 0.03 favoring A but without ruling out B, so we are including both solutions for analysis, and you can see the likelihood contours of all the 1, 2, and 3, let's say sigma intervals on the plot on the bottom. Then there are results of our combined analysis of run 1 plus partial run 2 dataset. The ambiguity of the delta gamma sign is constrained by the measurement of LHCb experiment. For the combination, we make use of the best linear unbiased estimate method, and you can see that both solutions or the differences between the 2 solutions are negligible even in the combination. So in the table below, in the 3 right columns, the red colors show the different number for each value. So for example, the phi-s for the combination of solution A is minus 0.087, and with solution B, it's minus 0.088. So all the differences are negligible. The combination is better shown on the plot on the next slide, where you can see the 7 and 8 TeV result in blue, then in green the 13 TeV result, and then in red the combined measurement or combined result of the run 1 plus partial run 2 analysis. These are 1 sigma confidence level contours for the most important parameters, the weak phase phi-s and the difference of the decay length delta gamma s. So there is a small comparison before and after, and also between the experiments. Very sorry for the different color code of the plots. The left plot is made by HFLAP group before the latest LHC results from all the experiments, and the right plot is the comparison of newest results from, I believe, all 3 experiments on the LHC. You can see we are still compatible with the standard model prediction and with the LHCb JPSI2 K plus K minus channel. We are slightly away from the combined LHC measurement and also from CMS. So to summarize that, we are not the B physics experiment, but we can still produce very impressive and competitive results. I've just shown you the latest update of the partial run-to analysis of the data from 15, 16, and 17, which is together 80 inverse femtobarns. And the results are consistent with those obtained in the previous Atlas analysis using 7 and 80 EV data, so we can combine them together. All our results are consistent or compatible with the standard model prediction. The analysis of the full run-to data, so another 60 inverse femtobarns, is currently ongoing. And please visit the TDK page of all our B physics public results. Thank you very much.
Thank you, Thomas. Really impressive. Do you any questions from the audience? Otherwise, we move to the FIS measurements from CMS now.
Okay, thank you very much. Let me stop the share.
Could people see the hand drying of the time? The text wasn't working when I wrote in the slide. No.
Sorry?
Could you see the time that I wrote?
Yes.
Okay. Because
yes,
the text
it was very nice. I see the first 5 minute label and then
okay.
the handwriting. Yeah.
So we can move on then with Enrico.
Yes, let me share the screen. Can you see the slides?
Yes.
So, hello, my name is Enrico Lusiani, and I'll be presenting the measurement of the CP violating phase FIES in the BS to JIP Sci-Fi channel at 13 TV by CMS. So let's start with a brief introduction. FIES is the CP violating phase arising from the interference between direct decays to a CP final state and decays through the BS anti-BS mixing. The standard model predicts this to be close to -2 beta S, where beta S is one of the angles in the unitary triangle, and equal to about -37 millirad, with the uncertainty below the millirad. However, new physics can change the value of FIES up to 10% via new particles contributing to the BS anti-BS mixing. Currently, the results agree with the standard model, but the experimental uncertainty is much higher than the theoretical one. The decay of FIES into JIP Sci-Fi is a good channel to measure FIES because there's no direct CP violating predicted, only one CP violating phase, and it's easy to reconstruct using the 2 muons and the 2 k. Also in the same analysis, we can extract several other interesting observables, such as the decay width, the difference decay width between the two eigenstates, the difference in mass, and the modulo of lambda, which is a parameter quantifying the CP violation. Let's now go to an overview of the analysis. The main issue in the analysis is that the final state is not a single CP eigenstate. So we need a time-dependent angular analysis to disentangle CP odd and CP even components. For this, we need a parameterization of the angles in the decay. On the right, we can see the one used by CMS, which uses CT, which is the LCT angle of the kaons in the phi rest frame, and theta and phi, which are the spherical coordinates of the muons in the JIP psi rest frame. We also need the proper decay time of the meson and its uncertainty, which is evaluated in each event. Finally, we need an accurate flavor tagging to infer the initial flavor of the BS meson, as the terms most sensitive to FIES in the decay rate depends on this. So for the tagging, we used an algorithm based on the opposite side muon, which uses the semi-leptonic decays of the second B in the event. For the analysis, it's important to not only have an accurate estimation of the flavor of the meson, but also a measurement of the accuracy for the flavor. For this, we trained our neural network so that the output is directly the mistake probability on each event. And we calibrated this output on data using B+ to J psi K+ self-tagging decays, as we can see in the plot on the right. Post-calibration, the average mistake is found to be close to 27%. Since we need a muon for the tagging, we developed a new trigger strategy to enhance the tagging efficiency, which is the number of tagged events over the total number of selected events. Our trigger requires a J psi decaying to 2 muons plus an additional muon, which is used for the tag. This trigger allows us to improve the tagging efficiency, but at the cost of a reduced number of selected single events. For example, the luminosity for this analysis is about 5 times the one used in a previous run 1 analysis, but the number of events is similar. We will see that this has important consequences in the precision of the measurement. Thanks to this new trigger strategy, the tagging efficiency is close to 50%. Let's now look a bit at the model. Without going into details, there are 3 main terms. The first is the signal, which contains the decay rate, of course, the efficiencies, and the PDF of our nuisance parameters. Then we have the combinatorial background, and then the peaking background, which comes from decays of bit 0 into J psi K star, where the pion was reconstructed as a kaon. Another possible source of background would be the lambda b to J psi kaon proton, but we estimated this to be negligible in our sample. The model is fitted to the data using an unbinned maximum likelihood fit, with inputs the 3 angles, the proper decay time, its uncertainty, the mass, the tag decision from the tagger, and the mistake probability. And from the fit, we can extract the physics parameter Φs, the decay width, the different decay width, the difference in mass, lambda, 3 amplitude for the different final states, and 3 strong phases. Here we can see the one-dimensional projection of our fit model. We can see the mass, the proper decay time, its uncertainty, and the angles. Here we show the systematic uncertainties for all the parameters in the fit. And in red, we evidence the leading systematic uncertainties for the main parameters. For Φs, these, for example, are the intrinsic bias of the model and the systematic uncertainty associated to the limited statistic we used to compute the angular efficiency. Here we can see the results of the fit. For Φs, we found it to be equal to -11 millirad, with a statistical uncertainty of 50 millirad and a systematic uncertainty of 10. Which is in agreement with the standard model. We also measured the different decay width, which again is in agreement with the standard model. The decay width and the difference in mass, which are consistent with the world average, and the modulo of lambda, which is consistent with having no direct CP violation, which will force its value to 1. The results are combined with those from the previous analysis at ICHEP, and the result of the combination are shown in this slide. We can see from the plot that the uncertainty of Φs is greatly reduced thanks to the increase in the tagging accuracy, but delta gamma S did not improve. because it's only sensitive to the total statistics and not to the tagging accuracy. Another thing to note in this plot is that the standard model prediction for delta gamma S shown in the plot is a fairly recent result, which greatly improved the uncertainty. In conclusion, we measured the CP violating phase Φs and the decay white difference delta gamma S using roughly 50,000 single events collected by CMS at 13 TeV using an integrated luminosity of about 96 inverse femtobarn. We developed a novel opposite side tagger based on deep neural network, which can predict the mistake probability on each event, which led to an improved precision in the Φs measurement. We combined the result with those from a previous analysis, yielding the result shown here, and both are consistent with the standard model prediction. The full article is available at the link shown here. Here is a small comparison with other LAC experiments. In the future, we plan to analyze the full round 2 dataset, adding a complementary trigger that requires a JPSI plus 2 charge tracks. And to improve even further the tagging performance, we will deploy an electron and jet-based taggers together with the current biome-based one. After this new trigger, we expect the precision of the measurement of Φs to improve by about 30% and of delta gamma S about a factor 2. Thanks for your attention. I'm done.
Thank you, Enrico. Questions from the audience? Yes, Niels, go ahead.
Hi, hello, I'm Niels from ICHEP. Thanks a lot for your interesting talk. I'm not sure if this is a question to you or maybe to the previous speaker, but can you maybe comment on how you see the difference in the delta gamma S, the decay width difference between Atlas and CMS?
Yes, we have noticed it, but we have no comment on it. We hope that the continuation of this analysis with the full round 2 dataset will shed some light on the difference.
Okay, thank you very much.
Any other question?
Sorry, just jumped in. I have a question on the fit projections that you have on page 7. Do you have a comment on how good they are? There seems to be some shifting around in cos theta t, for example.
Sorry, could you repeat?
This fit projection. I know they don't tell the whole story, so that makes sense. But there seems some shifting, for example, in the fit in cos theta t, where there is a linear trend, for example, or the low mass, the part of the J psi KK invariant mass.
Yes, of course, as you said, these are just projections, so we cannot infer too much. For the mass, we tried, we optimized the fit in 1 dimension, and it showed no issues there. We don't think we also tried different mass models and used them as a systematic. We don't think it's an issue for us, the not good projection, but okay. I hope this.
Yeah. Sorry. Yeah.
Any other comment or question to Enrico? Otherwise, let's move on now to charmless two-body B decays at LHCb from Davide Pazzini.
Yes, can you hear me?
Yes.
Let me share the slide. So good evening.
I can't see yet your slides.
Okay, sorry.
Oh, okay.
Now you can see?
Yes.
Okay, perfect. Good evening. Today I will give you a talk on the latest results of the measurement of CP violation in charmless two-body B-meson decays at LSCB. So the motivation of this analysis is that the CP observable are sensitive to the CKM angle alpha, gamma, beta, and beta S. And there are a rich set of physics processes that contribute to the generally called HB to HH decays, where the small h stands for kaon or thallium. We have 3 and penguin decay topologies and also neutral B mixing, as you can see from the diagrams in the bottom of the slide. So the key point is that in many of these diagrams, there are loops, and the effect of this loop is introducing hadronic uncertainty as additional parameter on the decay amplitude, and also make the CP observable sensitive to the new physics contribution. So what we want to measure in this analysis are the time-integrated CP asymmetry in B0 to K pi and BS to pi K decay, which are determined as reported in the top of the slide. So as the difference between the amplitude squared to the F bar and F state divided by the sum of the two terms. And also we want to measure the time-dependent CP asymmetry in B0 to pi pi and BS to KK, which are defined and reported in the middle of the slide. And in particular, we want to measure the free coefficient SF, SF, SEF, SF, and AF delta gamma, which are related to the direct CP violation, mixing induced CP violation, and the asymmetry related to the difference in a lifetime between the two mass eigenstates. So this free coefficient satisfy a unitary constraint, which is not imposed in the analysis, but you use it a posteriori as a cross-check to check the final results. So at the moment, the measure of the direct CP violation in the B0 to K pi and BS to pi K decay are dominated by the LSCB measurement performed at 1 inverse femtoban, as you can see from the table. And while the measure on C pi pi and S pi pi are well measured by both the B factories and the LSCB, using the B0 to pi pi decays, and the results between the 3 experiments are in very good agreement, as you can see both from the table and also from the typical SCP versus CCP plot reported in the bottom of the slide, where there are shown the results of the 3 experiments and also the world average. So the CP performed also a measurement of CKK and SKK using 1 inverse femtoban on the BS to KK sample, and the results are reported in the bottom of the slide. But for the moment, we don't have a measurement for A delta kappa KK. So the analysis that I'm going to present today is performed using the full run 1 data sample corresponding to 3 inverse femtoban. And the CP parameters are determined simultaneously using a multidimensional fit performed on the 3 different spectra K pi, pi pi, and KK. So in this slide, I point to the most important ingredient for the evaluation of the time-integrated, the time-dependent CP parameters. So for the first group, as you can see from the bottom of the slide, the rho asymmetry can be determined in the sum of the 3 components, one related to the CP asymmetry, and then we have a symmetry due to the final state detection symmetry and the production asymmetry. The first term is used as external input, while the second terms can be extracted directly from the RCP by means of a time-dependent fit. For the time-dependent CP violation, instead, the key points are the flavor tagging and the K-time resolution, which indeed diluted the true asymmetry, introducing two factors, and the decay time acceptance, which had large effect on the KK parameters, in particular on A delta kappa KK. So starting from the event selection, this is based on 2 different steps. The first is based on P the selection, which is used to separate the 3 final states, KK, pi pi, and K pi, in order to reduce the amount of cross-feed background contamination up to 10% of the signal yield. And then we perform a second step using a multivariate algorithm based on boost decision tree, used to reduce mainly the combinatorial background, optimized using the signal divided the square root of signal plus spectrum. So here On the right, you can see in the table the final yields for the 4 main signal mode. And in the bottom, instead, you can see the invariant mass distribution for the 3 different spectrum. In white, you can see the signal, which is clearly visible. In green, the combinatorial background, which is very small. And then in red, the free-body partially reconstructed mode. And in orange, the crossfit, which are very reduced. So starting from the flavor, going on with the flavor tagging, which is represent a key feature for the time-dependent analysis. In LCB, we have 2 different kind of algorithms. The same side taggers, which exploit the charge of the particle coming from the signal B fragmentation, which here on the right, there is a sketch with the flavor tagging algorithm available in LCB, and the top part is the one related to the same side taggers. So we have algorithm that exploit the pion, proton, and kaon. And then we have the opposite side charmer, which exploit the charge information of the decay of the opposite bit, which is in the bottom part of the sketch. So each of these algorithms provide the tagging decision and the mistag rate, which is quite important since enter directly in the dilution term that I mentioned before. And the performance on this algorithm can be estimated using the tagging power, which is the product of the tagging efficiency and the dilution factor squared, which is also quite important since it is inversely proportional to the statistical uncertainty of the CP asymmetry that we want to measure. Of course, in order to have an unbiased estimation of the mistag probability, we have to calibrate the information provided by the tagging algorithm, and this is performed on a specific control sample. Going on with the decay time resolution, this is calibrated using simultaneously the B0 to D pi and BS to DS pi decay, performing a time-dependent fit. So as you can see from the plot on the left on the slide, the symmetry in the B0 to D pi is basically reduced only by the dilution factor coming from the flavor tagging, since delta D is very small, and so the dilution from the decay time resolution is negligible. While for the BS, we have both the dilution factor. So from the first sample, we can estimate the dilution for the flavor tagging, and then looking at the difference, estimate the dilution from the decay time resolution, and then performing a calibration. Regarding the reconstruction efficiency, this is determined as function of the decay time using the B0 to K pi decays. Indeed, for these decays, the untargeted decay rate can be expressed as a pure exponential, so it's quite easy to retrieve the related reconstruction efficiency. And then for all the other decay signal mode, we basically correct the acceptance for the B0 to K pi for some factors that are estimated from fully simulated sample. Here on the right, on the slide, you can see the acceptance function for the B0 to K pi. Going to the last ingredient that I mentioned before, that are the production and the final state detection asymmetry. So the time-dependent asymmetry can be measured as described here in the top of the slide. So we have different contribution, a term related to the CP asymmetry, then a term related to the final state, 2 terms actually. The one term related to the detection asymmetry, and then another term related to the PID requirement applied to select the free spectra, and then the production asymmetry. As you can see, this last term is multiplied by a cosine term, so it can be extracted by means of time-dependent fit and measured directly on the B0 to K pi and BS to pi K decays. While for the other two terms, we have to take their value as external input. And so for the PID asymmetry is estimated using the D star plus to D0 pi decays, while the detection asymmetry is measured using the rho asymmetry of Cabippo favorite charm decays, D plus in K pi pi and D plus in K0 pi decays. And of course, at the end, these asymmetry are convoluted with the B0 to HH phase space in order to have a proper correction. Here in the bottom of the slide, you can see the value for this asymmetry for the B0 to K pi and for the BS to pi K decays. So going to the results, this is for the K pi final state. We obtained the most precise measurement from a single experiment. Here in the first box, you can see the value for the direct SCP asymmetry. And on the right, there is the invariant mass distribution for the K pi spectrum. And as I said, the production asymmetry can be determined directly by means of the time-dependent fit. And here I report also the value that we obtain for the B0 and the B sub S, and these are compatible with expectation. And we also perform a test on the standard model validity, assuming the U-spin symmetry. So we evaluate this discriminant delta, which is defined as the ratio between the SCP asymmetry between B0 and B sub S, plus the ratio of the branch diffraction of the decay mode times the ratio between the lifetime of the B0 and the B sub S. And we obtain the results reported here in the slide, where the first error is related to the fixed parameters, the fixed value report used for the evaluation, and the second term is related to the SCP asymmetry, and this is found to be compatible with the standard model expectation, which is 0. So moving to the PyPy and KK final state. So for the PyPy, also in this case, we obtain the most precise measurement from a single experiment. We basically have halved the uncertainty, both statistical and also systematics, obtained in the first LSCB analysis. Here you can see the results for CPyPy and SPyPy, where the first uncertainty is statistical and the second is systematics, along with their correlation. In the bottom of the plot, you can see the asymmetry for this spectra using only the opposite side and only the same side tag. Going to the KK final state, this was the very first measurement of A delta gamma KK. And performing a chi-square test, we obtained the strongest evidence of CP violation in time-dependent analysis for the BS sector, confirmed at more than 4 sigma. And here you can see the results for the various CP parameters with their statistical and systematic uncertainty. And as before, in the bottom of the slide, you can see the asymmetry plot for obtained using only the opposite side and only the same side tag. Going to the conclusion, the latest, today I show you the latest measurement of CP violation in B-meson decays to chargeless charge two-body final state performed at LSCB. Analysis is based on full run 1 corresponding to integrated luminosity of 1 inverse femtoban collected at 7 TeV and 2 inverse femtoban collected at 8 TeV. We got a significant improvement with respect to the previous measurement. We obtained the best measurement for CPyPy and SPyPy performed from a single experiment, as well as for the direct CP violation in B0 to KPy and BS2 PyK. And we also get the strongest evidence of CP violation in the BS sector at more than 4 sigma. So the analysis update based on run 2 data is close to be published. We expect that the combination RAR1 plus RAR2 exceed the 5 sigma for the CP violation in BS2KK. And then the target of the analysis are the summer conferences. So in the next few months, you should see a new presentation with the new results. So please stay tuned. And that's all from my side. So thank you for your attention.
Thank you, Davide. Questions, comments? Otherwise, thank you again, and remember to make questions at the Mattermost channel. So now we move to 3-body charmless BDKs in LHCb from Tomás Gramático.
Hello, can you hear me?
Yes.
Okay, great. Let me share my slides. Okay, is it working?
Yes.
Okay, great. Okay, so today, good evening, everyone. Today I'll be discussing the recent measurements of CP violation in charmless 3-body B-meson decays at LHCb. I'm Tomás Gramático, and I'm talking today on behalf of the LHCb collaboration. Today I will focus on 2 amplitude analysis, the amplitude analysis of B2 pi KK decays and the amplitude analysis of B2 3 pi n decays. Why is it interesting to perform such amplitude analysis? If we take a look at those 2 plots here, so those are the row asymmetries represented as Dalitz plane for, on the left, B to 3 pi on, and on the right, B to pi kk. And what we can see is that we can see the large row asymmetries. In the case of B to 3 pi on, there's even asymmetries where there is no known resonances. And so for those reasons, it's quite interesting to have a look at the, to perform the amplitude analysis. And also, so this analysis will use 3 inverse femtobarn of the data sample. And the decays are coupled through rescattering processes between a pair of pion and a pair of kaon. In both amplitude analysis, the isobar model will be used to describe the amplitude. So the isobar model consists of sum of products over the different contribution to describe the amplitude. The product contains the C term, which is CP evaluating and contains the weak dynamics, and the F term, which is CP conserving. And it's a product of a max line shape. Most of the time it will be a Bragg-Degner with an angular dependence and the barrier factors. In the case of B to 3 pion, the S-wave amplitude will be described by 3 different approaches. The first one is the isobar model we just discussed. Next, there's also the K-matrix formalism that will be used. This formalism conserves the 2-body unitarity when the dynamics is dominated by 2-body processes. And the third approach would be the quasi-model independent procedure, in which the S-wave will be described by bin, amplitude, and phases. And to separate the S-wave from the other contribution, we use the fact that the S-wave amplitude is constant in cos theta helicity. Now discussing further the amplitude analysis of B to pi kk. The signal yield is about 2,000 events for the B plus decay and 1,600 events for the B minus. This is the first time that the amplitude analysis of this mode has been performed. If we take a look at here on the left, the Dalitz plane for the B plus, and on the right, Dalitz plane for the B minus, we can already see, for example, in the green boxes, a clear CP evaluation effect when we compare the 2 distributions. The recent contributions here are limited. In the pi k channel, this can occur only through the penguin diagrams. For the KK resonances, they can come both from the tree level and the penguin diagrams. And the SS bar contribution is suppressed by Aussie rule. And the B plus and B minus are fitted simultaneously, which allows for CP validation. The Dalitz plane model that best describe the Dalitz plane is described here in this table, and I've put on the bottom left-hand corner the description of the fit fraction and the amplitude, the CP asymmetry, sorry. What we can see that the main contribution come from the single pole. The single pole is a non-resonant amplitude, which is a phenomenological description of the partonic interaction. Here's a description of the form factor. And another thing which should be mentioned is that the CP asymmetry of the rescattering is about minus 66%, and it's the dominant CP asymmetry that has been measured here. And the rescattering is described as a product of a single pole with the same description as above, with a scattering term here, where nu is the elasticity and the inelasticity, sorry, and delta is the phase shift. We have here on the right the projection of the number of entries on the invariant mass square of the pair of Kn. And looking at both the B plus results on the top and B minus on the bottom, we can see that the data described by the triangles is quite well modeled, the model being the line. And also, again, when we compare both distribution, the CP violation is clearly visible. And so, yeah, as I mentioned, the S wave, the CP violation is around minus 66%, which is the largest CP violation observation for a single amplitude. And this result is consistent with what is observed in B plus to 3 pi n. Another thing is that the B2 rho 1450 pi fit fraction is quite large at around 30%, which is larger than expected, as the rho is mainly decaying to 2 pi n's, and its contribution to the 3 pi n Dalitz plane is not so high. So we hope that the run2 data will give more, will help to understand this effect. We can move now to B2 3 pi n decays. The signal field here is of about 20,000 events. We have here the Dalitz plane distribution for the B plus on the left and the B minus on the right. Here we have two positively charged pions that can be assigned arbitrarily. And so both symmetry applies here. The model that best describes the Dalitz plane has as main contributions the rho 0 770 and the S wave. No CP violation was observed in the rho 0 case. Another thing that it was mentioning is that the F2 1270 has a CP violation of around 40%. Which is the first time that CP violation is observed in a process involving a tensor. And also the three approaches are in good agreement, as you can see on those tables. If we take a closer look to the rho omega region, we can see that there is no CP violation observed. When we integrate over cos theta L, as you can see on the projection here of the asymmetry on M low. But when we look at the asymmetry projected on cos theta LCT for the mass of the power of pi n below 0.78 gigaelectron volt here and above this value here, we can see that there is a significant CP violation, which changes sign on each side of the rho peak. And this effect cancels when we integrate over the ACT angle and or the invariant mass. In the PP S wave, in the pi S wave case, we can see from those projection of the amplitude square on the mass of the pair of pi n, on the invariant mass of the pair of pi n, we can see that the three different approaches are quite consistent with each other. And also there is a clear CP asymmetry below the K plus K minus threshold where it changes sign. And yeah, in the F2 1270 region, as I said, there is a CP violation, CP asymmetry measure of about 40%, as we can see also on this plot, which is the asymmetry projected on M low. This is again the first time that such an asymmetry has been observed in a process involving a tensor. And this result is robust with respect to the experimental and model uncertainties. To summarize, to better understand the rho asymmetries that were observed in B to pi kk and B to 3 pi n decays, challenging amplitude analyses were performed. In the case of B to pi kk, as you can see on those plots, a large CP violation was observed in the S wave contribution. which is consistent with what is observed in the B2 3-pion. For B2 3-pion, the S-wave contribution that is included in the model that described the Delts plane is well described by the three approaches, and they are consistent with each other. And there are three sources of CP violation that I would like to mention now, which are the CP violation in the S wave, in the interferences between the S and the P wave, and also CP violation in a D wave, which is the first time that this has been observed. And so, yeah, we expect that the run 2, we hope that the run 2 will bring new exciting insight on these decays. Thanks for your attention.
Thank you, Thomas. Questions, comments? I don't see any. So in that case, thank you again. And now we move to charmless B baryons.
Okay, thank you.
From Matteo Bartolini. Okay, I see the slides. You're muted. Okay.
Now, can you hear me?
Yes.
Good afternoon. So I will, in this presentation, I'll be talking to you about the latest results from HCB concerning the search for CP violation in charmless B-baryon decays. As you know, CP violation is well established in KB in the mesons decays and is well consistent with standard model predictions, but it has not been observed yet in B-baryons decays. Also, lambda B and XIB production is abundant in LHCb, and this gives the LHCb experiment an opportunity to study multi-body decays of B-flavored baryons. Multi-body final states are a very interesting place to search for CP violation because they can exhibit average resonance structures and therefore which can cause local CP violation effects. So these talks, I'll be talking in particular about this case with this topology where either lambda B or XIB, the case of proton and 3 mesons, which can be either pions or kaons. To this talk, 2 approaches will be used. Will be shown the standard ICHEP evaluation methods, which measures the asymmetry between the decay rate of a baryon and its charge conjugate, and a complementary approach, which is called typical product asymmetries, where one builds the odd observable by combining the momentum of the 3 final state particles in the matter rest frame. And by splitting the data samples according to the sign of the C variable and the flavor of the B baryons, one can measure these 2 CP violating asymmetries and also these 2 P violating asymmetries. These 2 approaches are complementary in the sense that they have different sensitivity to the physics. The standard CP violation is more sensitive to CP violating effects that have when the difference in strong phases of the interfering amplitude is large. On the contrary, the CP-TO asymmetries is more sensitive to effects where the difference in strong phase is small. They also show different sensitivity to systematic effect because by definition, the CP-TO asymmetry is not affected by reconstruction efficiency. and the potential behavior production asymmetries. Okay, so let me first start with the first experimental results concerning the sexual separation in lambda B to protons and tryptophanes. These using triple product asymmetries. These decays is a very rich resonance structures where contributions proceed mainly through these quasi-two-body decays listed here. The first measurement was released by LHCb in 2017 by using a sample of corresponding to material luminosity of 3 inverse femtobarn in run 1. And so both a phase-based integrated asymmetry was measured, where both the CP and P asymmetries are consistent with 0, and also asymmetries in the regions of the phase space to be more sensitive to local separation effect. So 2 schemes were defined: scheme A, where one beams on these resonances mainly, and also on the phi, which is the angle between the angle defined by the planes of this combination of these 2 particles. And one sees here that for the first time, one sees the first evidence of local CP violation effect at 3.3 sigma level. A similar approach, same approach, but with slightly different decays listed here, was used. It was measured in using the round 1 data set in 2011, 2012. And both the phase-based integrated asymmetries for the 3 channels are consistent with 0. And also the asymmetries in regions of the phase space, like for example, this decay, binning was done on these resonances, renouncing contributions of the resonances, and also on the angle defined by these particles. And no evidence for CP variation is found. Now, this decay, lambda B to protons and tryptophanes, was recently updated by adding also round 2 data sets corresponding to an integrated luminosity of 6.6 inverse femtobarn. Also, an optimized selection was used, which led to an HEADS which is 4 times larger than the previous analysis. 2 methods have been used: the standard triple product asymmetries and with optimized beaming scheme, and also an ambient energy test. So moving to the results for the phase-space integrated asymmetries, we see that for the CP asymmetries, it is consistent with 0. But we see a difference, we see a deviation of the 5.5 sigma level for the P symmetry. And whereas for the symmetries in specific regions of the phase space, the scheme A and B previously defined were also, in this case, were separated by a cut on this environment mass combination to enhance these particular contributions. And what we see here is that we see also no evidence for CP violation, where the high significance is reached in this, scheme B2, where the high significance is 2.9, which is slightly reduced with respect to the previous analysis. Now, complementary method is known as energy test method, which is, let's say, a model-independent approach. And this method is sensitive to local differences between 2 samples. And the test is defined here, where this psi is defined as follows, where D is an Euclidean distance between 2 candidates in the phase space defined by the combinations of by these coordinates in the phase space. Delta is a distance in scale in the phase space and is treated as a free parameters. So and T is large when there is a significant localized differences between 2 samples. So going to the results, what was done is that the sample was divided into 4 subsamples, which are linked to each other according to the following P and C transformation. And therefore one can do 3 tests, CP PO tests by combining the 1 and 4 subsample, and also the 2 and 3 as the second sample. A CP p-even test when the first sample is done by combining by adding 1 and 2 and 3 and 4, and a p-test where the first sample is obtained by adding 1 and 3 and 2 and 4. And the results show it was calculated for 3 different values of this delta. And the results shows that we have the highest significance in the CP p-even tests, but the combined significance is less than 3 sigma, whereas for the p tests we see a 5.3 sigma deviation from the p symmetry. And okay, now search for CP violation was also performed in these channels, but by using the standard CP asymmetries, and so the data sample also corresponds to 3 inverse femtobarn collisions collected in 2011 and 2012, and so this is the case that have been studied. And okay, and the method is the direct CP asymmetries, which whose formula is we are familiar with, and but this is a symmetry which can be, say, affected by track detection efficiencies and beyond production asymmetries, and therefore, in order to get rid of it, what they use is a control, a charmed control channel with similar kinematics and no CP violation expected in the standard model. And so one measures the following CP asymmetry, true CP asymmetries, where the fake CP asymmetries are eliminated at the first order. And so the asymmetries are extracted by an unbinary maximum likelihood fit, where the data are split according to the charge of the protons to extract the asymmetries. And now going to the results, we see that the integrated asymmetries are consistent with 0 for the channels. And so we see no evidence for CP violation. Also, but the search was also performed in specific regions of the phase space to search for local effects of the CP violation. And mainly 2 regions were defined, regions of the low invariant mass on the baronic pair, where we place a cut on this combination of protons and mesons, and also in specific regions of the phase space that contain quasi-2-body or 3-body decays. Now you see here the S-weighted distributions of some combinations of invariant masses, and you can see the resonances, well-known resonances. And the results also both for the low body mass regions and the quasi-2 body region shows that there is no evidence neither for the low body mass regions and in the quasi-2 body regions. This brings me to the conclusions of this talk, where I've shown you that multi-body decays is a very interesting place to search for CP violation due to the fact that they have rich phase-space structures. So for the moment, we have no evidence for CP violation in both in lambda B anxiety decays, but CP violation was found in this particular decays at 5.5 sigma level. What is interesting to note is that we already reached a precision of few percent in many channels, and a significant improvement is expected for run 3, because HCD we run at much high luminosities, and also because in particular, channels with finite state hadrons would benefit a lot from the removal of the L0 arbiter trigger. So that's all, and thank you very much for your attention.
Thank you, Matteo. Any questions? Okay, don't see any. So we finished the CP violation block, and we move to our last talk of this block and of the session with Salvatore Aiola on the dipole beam experiment.
Hello, can you hear me well?
Yes.
Okay, do you see the slides?
Yes.
Okay. So good evening, everybody. I'm gonna present today the dipole B project, which is a project aiming at measuring the dipole moments of electromagnetic moments of short-lived particle at the LHC. So first, just a quick introduction about electromagnetic dipole moments in particle physics. We know that all fundamental particles have non-zero magnetic dipole moments. Well, most, not all. There are fundamental particles with non-zero magnetic dipole moments. For example, the electron and most of the particles that we know of. Composite particles, such as hadrons, have a magnetic dipole moment that is stemming from their constituents. For example, for the proton and neutron, the values that we have are, from the theory, are in qualitative agreement with the experimental measurements. However, we have no experimental evidence of electric dipole moment of any fundamental particle. And we also have a limited experimental data for electromagnetic dipole moments of unstable particles, such as the tau, the lambda 0, and the lambda c. So why there is no electromagnetic dipole moment in fundamental particles? This is due to the fact that a permanent EDM violates both parity and time reversal symmetry. And assuming that the CPT theorem holds, this means that a permanent EDM violates also CP. This can, since we know that there is a CP violation in the standard model, this allows for a very tiny electromagnetic dipole moment, but this is so small that it's very far away from what we can experimentally probe. So if we do see an electric dipole moment in any fundamental particle, this is a direct evidence of beyond standard model physics, because it requires additional CP violation beyond what is in the standard model. So these are the current limits on the electric dipole moments of some of the particles. So the magenta bars from below are the limits coming from the expected values from the standard model. From above, the red bars indicates the current experimental limits, and we see that there is a large gap between the experimental limits and the standard model prediction. So there is a large region for potential discovery. In particular, I'm going to focus on these on some unstable particles, so particularly the lambda 0 and the charm variance, where we see that indeed the separation between the limits, the experimental limits and the standard model prediction is quite large. So how do we measure a particle electromagnetic dipole moments? We do this by measuring the precession of the particle dipole moments in a strong electromagnetic field. Of course, in order to observe precession, we need to have polarized beam of particles, and we must measure the initial and final polarization, so before and after the precession magnetic field, via the angular distribution of the decay products, since these are unstable particles. The tricky part of this measurement is that since these are unstable particles, they must travel in the electromagnetic field long enough to gain a sufficient precession before decaying. So I'm going to talk about two different measurements that we plan to do. One is about the lambda zero. In this case, we look for production in weak decays of heavy baryons, where the lambda zero is produced with the longitudinal polarization because of the violation of the weak decay. Then we will look for precession in the LHCb dipole magnet, and we reconstruct the lambda zero looking at decays that occur after the magnet before the tracking stations that are placed downstream of the magnet. The second part of the presentation will be related instead to another measurement that that aims at measuring the electromagnetic dipole moments of charm baryons. In this case, we will look for charm baryons produced promptly in fixed target proton tungsten collision. We know that these baryons are produced with the transverse polarization. This is because baryon is conserved in strong interactions. And we will look for precession through channeling in the bent crystal. I will explain how this is done. And then we plan to reconstruct the charm baryons inside the LHCb detector. So let's start from the lambda zero measurement. So as I mentioned earlier, we look for lambda zero that come from every baryon decay, for example, just for illustrative purposes, but it can be done in different decays. And here we will look for psi c that decays in lambda zero k pi. The lambda zero is polarized longitudinally due to the parity variation with decays. The k pi particles are reconstructed as long tracks. And their vertex coincides with the vertex of the psi c. So the vertex of the k pi can allow us to know where the psi c decayed, which is detached from the primary vertex. The lambda zero then will precess in the magnetic field of LHCb, and we will select only those lambda zero that decay after the magnetic field region. The proton and the pion coming from the decay of the lambda are reconstructed using T-tracks with the stations downstream of the magnet. The challenge is that we have a very limited momentum resolution for T-tracks. In fact, the proton and the pion momenta are measured based on the presence of the magnetic field that leaks out of the dipole magnet. This allows for a momentum resolution of around 20%. However, this can be improved using constraints from decay kinematics, because as I said earlier, we know that the decay vertex of the psi c, thanks to the reconstruction of the kaon and the pion in this case. So we used two benchmark study cases. One is lambda b that decays in J psi lambda, the other lambda c that decays in lambda 3 pi's. We choose these two ones because the reconstruction is easier than other decay channels, particularly the one with the J psi. However, these channels will not provide the best statistical significance because those are quite rare decays. So using these decays, we made a proof of principle that using LHC RAN2 data that we can reconstruct these decays. The promising progress has been done so far with the lambda zero mass resolution of around 1520 MeV/c². We use an MDA to improve the signal background discrimination and the resolution using boosted tree and artificial neural networks. And we also identified the main source of background, which is quite abundant for these decay reconstruction because of the secondary interactions with the material that occur in the beam pipe and in the superstructure of the tracking stations. We're also working on preparing a trigger strategy for LHC-RAN3. LHCb will take data using a fully software-based trigger. So this, of course, puts also some requirements, not only on the physics efficiency of the measurement, but also on the computing efficiency of the algorithms. So let's move to the other measurements that we plan to do. This is, as I said, this is based on particle channeling bent crystal. There's a long history of channeling physics, and so let me just say briefly what it is about. So channeling is a phenomenon whereby the trajectory of a charged particle is constrained in by the planes or axis of a crystalline solid. Channeling efficiency has been observed also in particles with 100 GeV of energy and even 6.5 TeV protons at the LHC. In particular, if the crystal is bent, then it can be used to guide the particle in the correct trajectory. The spin precession of polarized particle traveling to a bent crystal was theorized already in the late 70s, and it has been a proof of principle measurement that was done already in the 90s, measuring the MDM of lambda of the sigma baryon. And what we plan to do now is to use this similar technique to measure the electromagnetic dipole moment of the lambda c, with the challenge, of course, that the lambda c has a much shorter decay length. So the plan is to put a crystal in about 100 meters away from the interaction point of LHCb. So this first crystal is a crystal kicker that will deflect the beam halo towards a fixed target of tungsten. The protons will interact with tungsten target and produce lambda c that will enter a second pair of crystals that where the lambda c will undergo precession, and then we will measure the lambda c decays in the LHCb detector. Then there will be absorbers downstream of this experimental setup to absorb all the protons that did not interact with the tungsten target. So these are the projected limits on the electromagnetic dipole moment of the of several particles, so charm and the beauty baryons that can be measured in this configuration, and we see that they are quite competitive compared to what we have now. I mean, for most of these particles, we actually have no experimental limits at all. Then we have also projected limits on the magnetic dipole moments that would provide a very stringent QCD precision test. So the status of the project is that we have done an extensive R&D on long bent crystals. We had 2 crystals were tested, one made of germanium, one made of silicon. We have observed channeling in these long crystals with a good efficiency that is enough for the experiment, for our experiment. So in this figure, you see the peak at 0 corresponding to particles that traverse the crystal without entering the channeling condition, whereas at 16 millirad, you see the particles that come out of the crystal after being bent by the crystal structure. So in summary, the measurement of electromagnetic dipole moment of unstable particles that extends the LHC physics program is a unique program of measurements at LHC using the LHCb detector. So far, we have, so regarding the lambda 0 measurement, we have achieved the reconstruction of decays beyond the magnetic region using an MDA to discriminate signal background, and we have studied the background sources. And the next steps is to study the helicity measurement resolution and define and propose a trigger strategy for RAN3. Regarding the fixed target setup for the charm baryon measurement, we have long bent crystal prototypes that have been been tested and are good candidates for this experiment. Then we have done some preparatory studies and simulations in LHCb. Machine layout has been designed by the experts of LHC, of the accelerator. So the next steps will be to prepare a technical design report. And this is all I have for today. Thank you very much for your attention.
Thank you, Salvatore. Questions? Comments?
This is Alexei Petrov.
Go ahead.
Hi. So this the channeling. I'm not a specialist in channeling bent crystals, but this seems to be quite exciting technique. Would it work for leptons as well? I mean, for instance, if I would like to measure, you know, MDMs of tau leptons, for instance.
Yeah, certainly. In fact, I didn't talk about this because of time constraints, but there is indeed a proposal. I can send you a link to a paper that was published a few months ago about a proposal to use a similar technique to apply it to the measurement of the tau electromagnetic dipole moment. It is more challenging because of how the tau decays, so it's a more challenging measurement. It requires a lot more statistics. But yes, certainly it can be done also for leptons.
Cool. I would appreciate it. Thank you.
Yeah.
Any other question? I have a couple. So the idea is to start by the start of run 3 then?
No, the idea is to start perhaps during run 3. So maybe to install these, the equipment should be possible. Maybe, I mean, with this we have to still negotiate with the accelerator expert, but certainly we will not be ready for the start of run 3. So if we manage, we do it in one of the technical stops, end of year technical stops that during run 3. Otherwise, it will be done in run 4.
Okay, and another thing due to my ignorance, so what can you comment on possible new physics models that would lead to EDM?
I think there could be many. I mean, it just requires additional CPU violation in the standard model. So I think pretty much any model that adds CPU violation to the standard model could have an electromagnetic dipole moment. I think it's not difficult to have this in a model. It just requires more CPU violation.
More CPU violation, okay. So are any other questions? So otherwise, this is the finish of the session 2 of the Quark and Lepton flavor track. Tomorrow, the third session, the premiere will be in the morning, starting at 8 a.m. European time. So we moved to the morning for Thursday and Friday. So see you tomorrow. Thank you all. For those who want to stay here to discuss further, the Zoom room will be open for a while.
Thank you.